There's something almost magical about looking up at the night sky, a feeling that stretches back to the very dawn of humanity. The stars, the planets, the vast swirling galaxies, they're not just scattered randomly across the cosmos. What if I told you they're part of an intricate, almost deliberate design, a hidden language written in the fabric of space itself, waiting to be deciphered? This isn't just poetry or imagination. The universe operates with a precision that borders on artistry, and the patterns we see, from the spiraling arms of distant galaxies to the delicate fractals of nebulae, are clues to something far grander. These celestial designs aren't accidents, they're blueprints revealing the deepest secrets of how everything came to be. Think about the last time you stared at the stars. Maybe you traced the lines of a constellation, connecting the dots to form a shape, a bear, a hunter, a dragon. But what if those connections go even deeper? What if the universe itself is structured in ways that mirror the very mathematics we use to understand it? From the golden ratio found in the curl of a galaxy to the fractal repetitions in cosmic dust clouds, there's an order to the chaos. Scientists have spent centuries unraveling these mysteries, and what they've found is astonishing. The same patterns that govern the growth of a seashell or the branching of a tree also shape the birth of stars and the expansion of the cosmos. It's as if the universe is whispering its secrets to us, if only we know how to listen. This journey isn't just for astronomers or mathematicians. It's for anyone who's ever felt that spark of wonder under a starry sky. By the time we're done, you'll never look at the night the same way again. We'll explore how these celestial patterns hold the keys to understanding everything from the formation of planets to the fate of the universe itself. You'll see how ancient cultures instinctively recognized these designs, weaving them into myths and legends long before modern science confirmed their significance. And most of all, you'll come away with a sense of awe, a realization that we're part of something vast, beautiful, and profoundly interconnected. So let's begin. The cosmos is waiting to reveal its story, and it starts with the patterns written in the stars. The golden ratio is more than just a number, it's a fingerprint of creation, etched into the fabric of the cosmos. Picture the spiral of a galaxy, its arms unfurling with perfect grace. That elegant curve isn't random. It follows the same mathematical rhythm as a seashell or a sunflower's seeds, the golden ratio, roughly 1.618. This number doesn't just show up in art or architecture. It's woven into the very structure of the universe. Take the Milky Way. Its swirling arms aren't chaotic. They grow outward in a pattern that mirrors the Fibonacci sequence, where each number is the sum of the two before it. 1, 1, 2, 3, 5, 8. The sequence builds, just like the galaxy's spiral expands, following the golden ratio's invisible guide. But it doesn't stop there. Look at the way planets and moons move. Some orbits align with this same ratio, as if gravity itself dances to this ancient mathematical tune. Saturn's rings, for example, divide into sections that reflect the golden ratio's proportions. Even the spacing between planets in our solar system loosely echoes this pattern, though scientists still debate whether it's meaningful coincidence or something deeper. Skeptics argue that with infinite possibilities, some patterns are bound to emerge by chance. Yet when we see the golden ratio appear again and again, from the microscopic to the cosmic, it's hard to dismiss as mere accident. What if this ratio is more than just a quirk of math? What if it's a fundamental law, a blueprint the universe uses to build itself? Ancient thinkers like Pythagoras believed numbers were the language of reality, and modern science keeps uncovering evidence that supports this idea. The golden ratio isn't just a pretty shape, it's a recipe for efficiency, a way for nature to grow and organize with minimal energy. That's why it appears in hurricanes, fern fronds, and galaxies alike. It's the universe's way of balancing chaos and order, creativity and structure. And if that's true, then every spiral in the night sky isn't just a sight to behold. It's a message, a clue to how everything fits together. Now imagine zooming in even closer, where the cosmos reveals another layer of its artistry. Beyond the golden ratio, there's a hidden geometry that repeats itself across scales, fractals, the infinite patterns that shape everything from lightning bolts to the branching veins of the universe itself. Fractals are nature's way of repeating itself, an endless echo of shapes that look the same no matter how far you zoom in or out. Picture a bolt of lightning, jagged and electric, splitting into smaller forks that mirror the larger strike. Now imagine that same branching pattern stretching across the cosmos, etched into the swirling arms of nebulae or the tangled web of galaxies. This isn't just coincidence. The universe loves repetition, and fractals are its signature. Take the Mandelbrot set, a mathematical masterpiece of infinite complexity. Its swirling edges look eerily similar to the structures we see in star-forming regions, where clouds of gas collapse into new suns. It's as if the same blueprint is used for both a mathematical formula and the birth of a star. But why does this happen? The answer lies in efficiency. Nature thrives on simplicity, reusing the same patterns because they work. A river's delta branches like a tree, which branches like our lungs, which branch like the filaments of the cosmic web, the vast, invisible scaffolding that holds galaxies together. Even the distribution of dark matter, the mysterious substance that makes up most of the universe's mass, seems to follow fractal-like arrangements. Scientists are just beginning to unravel how these patterns influence the way galaxies cluster together, like beads on an invisible string. Some researchers even think fractals could help explain the large-scale structure of the cosmos, revealing hidden connections between the tiniest quantum fluctuations and the grandest galactic superclusters. What's truly mind-bending is how fractals blur the line between chaos and order. A snowflake might seem random, but its intricate symmetry follows strict mathematical rules. The same goes for the cosmos. What looks like disorder, exploding stars, colliding galaxies, swirling dust, often conceals an underlying harmony. Ancient cultures sensed this duality, weaving it into creation myths about serpents swallowing their tails or worlds built on cycles within cycles. Today, we have the tools to see these patterns for what they are, clues to a deeper truth. The universe isn't just built on laws, it's built on rhythms, repetitions, and self-similar designs that transcend scale. Now, shift your perspective from the infinite to the perfectly balanced. If fractals show us the universe's love of repetition, then orbital symmetry reveals its obsession with harmony. Planets don't just move, they dance, tracing ellipses so precise they've inspired poets and physicists alike. Johannes Kepler, the astronomer who first decoded these celestial motions, called them the music of the spheres. And he wasn't entirely wrong. The gravitational pull between planets and stars creates resonances, rhythmic alignments that keep solar systems stable over billions of years. Look at Jupiter's moons, locked in orbits where one moon's year is exactly twice as long as another's, a cosmic timekeeper ticking in perfect sync. Even the gaps in Saturn's rings follow this musical logic, cleared by the gravitational echoes of its orbiting moons. This symmetry isn't just beautiful, it's essential. Without it, planets would spiral into chaos, colliding or flinging into the void. The fact that we exist at all is proof of this delicate balance. But here's the mystery. Why does the universe favor such harmony? Some scientists argue it's a natural outcome of gravity's laws. while others wonder if deeper, undiscovered principles are at work. One thing is certain: whether it's the fractal swirl of a galaxy or the perfect ellipse of an orbit, the cosmos speaks in patterns, and the more we learn to listen, the more its secrets unfold. Symmetry isn't just a feature of our solar system, it's a cosmic signature, written into the very fabric of planetary motion. Picture Earth's elliptical path around the Sun, a smooth curve that repeats like clockwork year after year. This isn't happenstance, it's gravity's masterpiece, a delicate balance between momentum and pull that keeps planets from spiraling into chaos. Johannes Kepler cracked this celestial code 4 centuries ago with his 3 laws of motion, revealing how planets speed up as they near the Sun and slow down as they drift away, tracing orbits that obey precise mathematical relationships. But here's the astonishing part: this isn't just about our cosmic neighborhood. The same gravitational choreography plays out in distant star systems, where exoplanets waltz around their suns in rhythms that feel eerily familiar. Take Saturn's rings, those dazzling bands of ice and dust. They're not a continuous sheet, but a series of gaps and divisions, like grooves on a cosmic record. These spaces aren't random. They're carved out by gravitational resonances, places where the tug of Saturn's moons creates voids, like a pendulum swinging in perfect time. The Cassini division, that striking dark band in the rings, exists because particles there orbit twice for every single orbit of the moon mimas. It's a gravitational echo, a silent drumbeat that shapes the rings into art. And this phenomenon isn't unique to Saturn. Jupiter's moons Io, Europa, and Ganymede are locked in a similar dance, their orbits synced in a 1:4 ratio, a celestial metronome ticking across the ages. Yet perfection is rare in the cosmos. Even in this symphony of symmetry, there are discords, collisions, asteroid strikes, the gravitational nudge of passing stars. Uranus tilts wildly on its side, likely knocked askew by some ancient impact. Mercury's orbit wobbles ever so slightly, a quirk Einstein used to prove relativity. These imperfections remind us that the universe isn't a static painting but a dynamic, evolving sculpture. But here's the mystery: despite the chaos, the underlying order persists. Exoplanet hunters have found worlds in far-flung systems orbiting in resonant chains, their paths harmonized like notes in a chord. Could this mean symmetry isn't just a local rule but a universal preference, a way for gravity to sculpt stable, enduring systems? Now, shift your gaze from the clockwork precision of orbits to the swirling, painterly chaos of nebulae. At first glance, these cosmic clouds seem like the opposite of symmetry, a riot of color and form, where stars are born and die in spectacular bursts. But look closer. Even here, in the apparent anarchy of stellar nurseries, patterns emerge. The pillars of creation in the Eagle Nebula, those towering columns of gas, aren't random sculptures. They're shaped by shock waves and magnetic fields, their fingers stretching outward in fractal-like branches. The Helix Nebula, with its eerie green glow, expands in near-perfect concentric rings, as if blown by some celestial glassblower. And the Butterfly Nebula, its twin lobes mirror each other with an almost artistic balance, despite the violent stellar winds carving them. What's breathtaking is how these structures bridge order and chaos. A nebula might seem like a cosmic accident, but its forms obey the same physics that govern planets and galaxies. Turbulence creates whirlpools within the gas, and magnetism sculpts streams of charged particles into braids and loops. Even the randomness has rules, and just as Kepler saw music in the planets, there's a rhythm here too, a pulse of creation and destruction, where symmetry emerges from the storm. Perhaps that's the universe's greatest secret. Beneath the surface of every beautiful mess, there's a design waiting to be seen. Nebulae are the universe's grandest art galleries, where gas and dust transform into breathtaking masterpieces under the brushstrokes of gravity and light. Take the pillars of creation, those colossal towers of cosmic dust in the Eagle Nebula. From a distance, they look like a frozen tidal wave, but zoom in, and you'll see each pillar is a stellar nursery, cradling newborn stars in its swirling folds. The sheer scale is humbling. Those pillars stretch trillions of kilometers tall, yet they're sculpted by something as delicate as starlight. Radiation from nearby stars erodes the gas like wind-carving sandstone, revealing pockets of dense material where stars ignite. It's a dance of creation and destruction where every flicker of light reshapes the landscape. Then there's the Butterfly Nebula, with its twin wings of glowing gas stretching symmetrically into space. This isn't just a pretty accident. Those wings are shaped by a dying star at its center, expelling material in opposing jets at speeds topping 600,000 kilometers per hour. The symmetry, that's physics in action. The star's magnetic fields channel the outbursts into mirror image flows, like a spinning top releasing energy in perfect balance. Even the Helix Nebula, often called the Eye of God, reveals an astonishing precision. Its nested rings, glowing in eerie blues and reds, are the expelled layers of a sun-like star, puffing away in rhythmic pulses over millennia. What seems chaotic is actually a slow, deliberate unraveling, a star's final performance staged across light years. But these nebulae aren't just cosmic eye candy. They're time capsules preserving the recipes of star formation. The chemicals we find in them, oxygen, carbon, even the building blocks of water, are the same elements that eventually form planets and, in some cases, life. When a star dies, it scatters these ingredients back into space, seeding future generations of stars and worlds. That's why astronomers study nebulae so intently. They're like ancient libraries, their structures encoding the history of the cosmos. The pillars of creation, for instance, show us how shockwaves from supernova can trigger star birth, while the Butterfly Nebula teaches us how stars recycle their material into the galaxy. Now imagine stretching this artistry to an even grander scale. Beyond individual nebulae, the universe is woven together by vast, thread-like structures called cosmic filaments, the invisible scaffolding of the cosmos. These filaments connect galaxies like beads on a string, tracing patterns so immense they defy comprehension. And just like nebulae, they hide a secret. Their delicate balance of gravity and dark matter shapes everything we see. Cosmic filaments are the hidden architecture of the universe, the silent scaffolding that holds everything together. Picture an impossibly vast spiderweb, its threads stretching across billions of light years, each strand pulsing with galaxies like beads on a string. This isn't just a poetic image, it's the reality of our cosmos. These filaments, woven from dark matter and ionized gas, form a labyrinthine network that connects galaxy clusters in a delicate balance of gravity and motion. Without them, the universe would be a formless void, its matter scattered randomly like dust in the wind. Instead, we see order, a sprawling, intricate design that emerged from the chaos of the Big Bang. Scientists first glimpsed this structure by mapping the positions of thousands of galaxies, revealing patterns that defied randomness. The Sloan Digital Sky Survey, one of the most ambitious astronomical projects ever undertaken, showed us the universe in 3 dimensions, and what we saw was astonishing. Galaxies weren't just sprinkled randomly, they clustered along these filaments, drawn together by the invisible pull of dark matter. Simulations of cosmic evolution, like the Millennium Run, recreate this process in stunning detail. They show how tiny fluctuations in the early universe, density variations no larger than a grain of sand, grew over billions of years into the filaments we see today. Gravity amplified those microscopic ripples, sculpting them into highways of matter that funnel galaxies toward dense nodes, the superclusters where thousands of galaxies gather like cities in a celestial metropolis. But what's truly mind-bending is the scale. A single filament can stretch for hundreds of millions of light years, a thread so vast it dwarfs our entire Milky Way. The Hercules Corona Borealis Great Wall, one of the largest known structures, spans 10 billion light-years, a staggering 1/10 the observable universe. These aren't just abstract shapes, they're dynamic, evolving rivers of gas and dark matter, where galaxies ride the currents like leaves on a stream. And at the intersections of these filaments, where the cosmic web knots together, you'll find the most massive objects in existence, galaxy clusters glowing with the heat of a million suns, their gravity bending space itself. Now shift your gaze to the brightest beacons along these filaments, quasars. These dazzling objects, powered by supermassive black holes, act like cosmic lighthouses, their light piercing through the darkness of space. Quasars aren't just random fireworks, they cluster along filaments too, tracing the same invisible pathways as galaxies. Their intense radiation ionizes the gas around them, lighting up the filaments like neon signs in a cosmic city. By studying quasars, astronomers can map the filaments in even greater detail, revealing how these structures channel matter and energy across the universe. Some quasars are so ancient their light has traveled nearly 13 billion years to reach us, offering snapshots of the cosmic web in its infancy. What's emerging is a picture of breathtaking interconnectedness. The filaments aren't just backdrops, they're active participants in the universe's evolution, shaping where and how galaxies form. Without them, stars might never have ignited, planets might never have coalesced, and we might never have existed to ponder their beauty. So the next time you look up at the night sky, remember, you're not just seeing stars, you're glimpsing a single thread in the grandest tapestry of all, a tapestry still being woven, one filament at a time. Quasars are the universe's most brilliant beacons, shining with the intensity of 1 trillion suns from the edges of space-time. Yet some of these cosmic powerhouses seem to be playing a game of cosmic connect the dots, aligning in ways that defy logic. Imagine standing in a field of lighthouses, scattered randomly across a continent, only to realize their beams are all pointing in the same direction. That's the baffling puzzle quasars present. Across billions of light years, their rotational axes sometimes line up with eerie precision, as if guided by an invisible hand. This shouldn't happen. According to our understanding of the cosmos, matter distributes randomly on such vast scales, leaving no room for coordination. Yet here we are, staring at a celestial mystery that refuses to fit the script. One leading theory points to cosmic filaments, those gargantuan threads of dark matter we explored earlier as potential puppet masters. If quasars form preferentially along these filaments, their alignment might reflect the filament's own structure, like compass needles tracing a magnetic field. Simulations show that the gravitational tug of these filaments could nudge quasars into loose synchrony over time, but the latest observations push even this idea to its limits. Some quasar groups align more precisely than filaments alone can explain, their axes matching to within a few degrees. That's like tossing 1,000 pencils into the air and having them all land pointing northeast. The odds, astronomers calculate them at less than 1 in a million. Then there's the wild card, primordial magnetic fields. These hypothetical relics from the Big Bang could span the entire universe, imprinting directionality on matter as it formed. If such fields exist, they might have gently rotated quasar-forming gas clouds in their infancy, leaving a lasting signature in their spins. It's a tantalizing idea, but detecting these faint magnetic whispers across cosmic time remains a monumental challenge. Skeptics, meanwhile, argue we're seeing patterns where none exist, that given enough quasars, some apparent alignments are inevitable. Yet as telescopes like the European Space Agency's Gaia mission map ever more quasars, the anomalies persist, nudging us toward a humbling truth. The universe might be more interconnected, more orchestrated than we ever imagined. What makes this mystery so thrilling is its scale. These alignments span distances so vast that light hasn't had time to travel between them since the Big Bang. That means no signal, no force we know of could have synchronized them, unless, and this is where physics gets spine-tingling, there's something fundamental we're missing. Could undiscovered particles mediate long-range interactions? Does space-time itself have a hidden grain, like wood, guiding structures along preferred directions? Or is this a clue that the cosmos is even stranger than we've dared to suppose? Now, shift your focus from these enigmatic alignments to another cosmic metronome, pulsars. These spinning neutron stars tick with a precision that rivals atomic clocks, their rhythmic pulses slicing through the darkness like lighthouse beams. Yet even here, in what should be nature's most predictable timekeepers, we find whispers of deeper mysteries. Pulsars are nature's most precise timekeepers, spinning with a rhythm so steady it puts even our finest atomic clocks to shame. Born from the explosive deaths of massive stars, these neutron stars pack the mass of a sun into a sphere no wider than a city, their gravity so intense it crushes atoms into a sea of pure neutrons. Yet despite their violent origins, pulsars are models of cosmic discipline. Take the Crab pulsar, the remnant of a supernova witnessed by Chinese astronomers in the year 1054. It spins 30 times every second, beaming radiation across space like a lighthouse with unerring precision. Each pulse arrives right on schedule, so predictable that scientists use them to navigate spacecraft and test Einstein's theory of relativity with pinpoint accuracy. But how do these cosmic metronomes maintain such flawless timing? The answer lies in their incredible density. A pulsar's rotation is like a spinning ice skater pulling their arms in. The tighter they compress, the faster they spin. When a massive star collapses into a neutron star, its rotation speeds up dramatically, some reaching hundreds of revolutions per second. And with no friction to slow them down, they just keep ticking, their beams sweeping across the cosmos like the hands of a celestial clock. The only thing that can disrupt this rhythm is a glitch, a sudden, tiny jump in rotation caused by starquakes or changes in the pulsar's interior. Even these are rare, making pulsars some of the most stable objects in the universe. Now imagine two pulsars locked in a gravitational embrace. Binary pulsar systems where two neutron stars orbit each other are laboratories for extreme physics. Their dance is so precise that astronomers can measure the tiniest distortions in spacetime caused by their motion. The first such system discovered, PSRB 1913+16, proved Einstein's prediction that orbiting stars emit gravitational waves ripples in the fabric of space itself. Over decades, the pulsar's orbits have decayed by exactly the amount relativity predicts, a triumph of theory meeting observation. But binary pulsars aren't just cosmic experiments, they're also storytellers. By tracking their pulses, we've learned how neutron stars can steal matter from companions, how magnetic fields evolve over millennia, and even how some pulsars eventually spiral together in spectacular collisions that forge gold and platinum in their wake. What's truly mesmerizing is how these cosmic clocks connect to our daily lives. The Global Positioning System, or GPS, relies on atomic clocks to pinpoint locations on Earth, but those clocks must account for relativity's time-stretching effects, verified by pulsars. Without these distant spinning stars, our smartphones' maps would drift off course by kilometers. Pulsars have even been proposed as interstellar navigation beacons, their pulses forming a galactic GPS for future spacefarers. And then there's the big question: what happens when a pulsar spin finally winds down? Over billions of years, even these mighty rotators slow, their beams fading until they vanish into the dark. But their legacy endures. The heavy elements they create in collisions become part of new stars, planets, and perhaps even life. So the next time you check the time, remember, somewhere in the cosmos, a pulsar is keeping perfect rhythm, a heartbeat echoing across the ages. Binary star systems are nature's grandest ballets, a celestial pas de deux where two stars whirl around each other in an endless embrace. Picture two massive dancers, their movements dictated by gravity's invisible strings, pirouetting through space with breathtaking precision. Some binaries, like Algol in the constellation Perseus, perform a cosmic eclipse routine where one star passes in front of the other, dimming their combined light like clockwork every few days. Others, like the famous Sirius system, feature a brilliant main star with a faint white dwarf companion, a ghostly remnant of a once mighty sun. These pairings aren't just beautiful to observe, they're laboratories for understanding stellar life cycles, revealing how stars age, exchange mass, and sometimes meet dramatic ends. But the real spectacle begins when binary stars get too close. In systems like VFTS 352, two massive stars orbit so tightly their surfaces nearly touch, distorting each other into teardrop shapes as they share a swirling shroud of gas. Over time, their dance can turn deadly. As they spiral inward, gravitational waves, ripples in space-time carry away energy, sealing their fate. Eventually, they collide, triggering explosions so violent they can outshine entire galaxies. These mergers, called kilonovae, are cosmic forges, spewing out gold, platinum, and other heavy elements that someday might end up in jewelry or electronics on Earth. It's a reminder that even the most distant stellar dramas are intimately connected to our world. Now, imagine a planet caught in this gravitational tango. Binary stars with orbiting planets like Kepler 16b create landscapes straight out of science fiction worlds with two suns in their skies, casting ever-shifting shadows. These planets face extraordinary challenges. Their orbits must navigate the competing pulls of two stars, avoiding paths that would fling them into space or plunge them into stellar flames. Yet somehow, against the odds, some survive. Astronomers call these circumbinary planets, and their existence forces us to rethink how planetary systems form and endure. The habitable zone, the region where liquid water could exist, becomes a moving target, stretching and warping as the stars swing around each other. Could life arise under such chaotic conditions? It's a tantalizing question, pushing the boundaries of what we consider possible in the cosmos. What makes binary stars so fascinating isn't just their variety, but what they teach us about gravity's subtle artistry. Their orbits are exquisitely sensitive to mass, distance, and even the fabric of spacetime itself. By studying them, we've confirmed Einstein's predictions about gravitational waves and uncovered hidden stellar phenomena, like vampire stars that siphon material from their companions. Each system is a puzzle, its motions encoding secrets about the universe's fundamental forces. And as telescopes grow more powerful, we're finding binaries in every corner of the galaxy, some serene, others volatile, all whispering clues about how stars live, die, and shape the cosmos around them. Now, shift your gaze from these stellar duets to the oldest light in the universe, the cosmic microwave background radiation. This faint glow, lingering from the Big Bang, carries imprints of the universe's infancy, patterns that might hold the key to understanding everything that came after. The cosmic microwave background is like a baby picture of the universe, a faded photograph taken when everything was just 380,000 years old. This afterglow of the Big Bang fills every corner of space, a whisper of heat left over from creation itself. But it's not perfectly smooth. Tiny variations in temperature, fluctuations no larger than 1 part in 100,000, paint a speckled pattern across the sky. These aren't random blemishes, they're cosmic blueprints, the seeds from which all galaxies, stars, and planets would eventually grow. When satellites like Planck mapped these variations with exquisite precision, they revealed something astonishing. The fluctuations follow a mathematical spectrum so precise it could only come from quantum vibrations in the universe's first moments. It's as if we're hearing the echo of creation's first breath. One of the most intriguing mysteries lies in what scientists call the cold spot, a region of the CMB significantly cooler than its surroundings, spanning nearly 1 billion light-years. At first glance, it might seem like a random fluctuation, but the odds of such an extreme anomaly appearing by chance are less than 1 in 50. Some theorists suggest it could be evidence of a collision with another universe during cosmic inflation, a bruise left by a parallel reality brushing against our own. Others propose it's a vast cosmic void, an emptiness so profound it stretches the fabric of space-time, cooling light that passes through it like air expanding over a mountain. Then there are the unexpected alignments, large-scale patterns in the CMB that seem to defy the cosmological principle, which states the universe should look roughly the same in all directions. Dubbed the axis of evil by skeptical researchers, these alignments have sparked debates about whether our standard model of cosmology is missing something fundamental. Now shift your gaze from these primordial whispers to the darkest enigmas in the cosmos, black holes, specifically the strange geometry of their shadows. When the Event Horizon Telescope captured the first image of a black hole in 2019, the world saw a fiery ring of light encircling a perfect circle of darkness. That dark center isn't just empty space, it's a shadow, a region where gravity is so intense that not even light can escape. But here's the twist: the size and shape of that shadow aren't arbitrary. They're dictated by Einstein's equations, warped by the black hole's spin and the fabric of spacetime itself. A non-rotating black hole would cast a perfect circular shadow, but most black holes whirl like cosmic tops, stretching their shadows into asymmetrical ovals. What makes these shadows so fascinating is how they probe the limits of physics. The boundary of a black hole's shadow, its photon ring, is where light orbits in a desperate ballet, neither escaping nor falling in. These photons trace the very edge of reality as we know it. Some theories predict that if quantum gravity effects alter spacetime near a black hole's core, these shadows might reveal subtle fingerprints in their structure. Already, researchers are analyzing the Event Horizon Telescope's data for tiny deviations from Einstein's predictions, hunting for clues to how gravity behaves under the most extreme conditions. It's like using a shadow to deduce the shape of an unseen object. Only here, the object bends the rules of space and time. The connection between the cosmic microwave background and black hole shadows might not be obvious at first, but both are cosmic canvases where the universe inscribes its deepest secrets. One shows us the aftermath of creation, the other, the boundaries of destruction. Together, they remind us that the cosmos speaks in geometry, a language of perfect curves, mysterious alignments, and hidden symmetries waiting to be decoded. And with every new observation, we're learning to listen just a little better. That fiery ring of light surrounding a perfect circle of darkness, the first image of a black hole's shadow, wasn't just a triumph of technology. It was a direct window into the heart of spacetime's most extreme warping. When the Event Horizon Telescope revealed the shadow of Messier 87's supermassive black hole, the world saw Einstein's predictions made visible, a glowing ring of photons trapped in orbit, their light bent into a halo by gravity's relentless grip. But what's astonishing isn't just the confirmation of relativity, it's the tiny details that might rewrite the rules. The shadow's crisp edges, its slight asymmetry, even its size, all of these are clues written in light and darkness, waiting to be decoded. Take the shadow's shape. A non-spinning black hole would cast a near-perfect circular shadow, but M87's monster whirls at dizzying speeds, flattening one side of its silhouette like a spinning top pressed under glass. This distortion isn't random, it's a precise measurement of the black hole's angular momentum, a property that could reveal how it grew. Did it feast on gas spiraling in from a single direction, or did it merge with other black holes, each collision adding a wild spin? The shadow holds the answers, and then there's the shadow's size. According to general relativity, a black hole's shadow should be about 2.6 times wider than its event horizon, a ratio so exact it's become a cosmic ruler. Any deviation from this could hint at forces beyond Einstein's equations, perhaps even traces of extra dimensions curled tightly around the black hole's core. But here's where it gets stranger. Some theorists propose that black hole shadows might act like holograms, encoding information about their past in their geometry. Just as a pebble dropped in a pond creates ripples that remember its size and shape, a black hole's shadow could retain echoes of the matter that formed it. This idea, called the cosmic holography principle, suggests that the three-dimensional universe we see might be a projection of information stored on two-dimensional surfaces, like shadows on a cave wall. If true, studying these dark silhouettes could become a way to read a black hole's history, from its violent birth to the galaxies it's devoured over eons. Now shift your gaze from the darkness at a black hole's heart to the luminous web of galaxies surrounding it. Just as black holes sculpt space-time, galaxy clusters assemble into vast, fractal-like tapestries repeating patterns that mirror the universe's deepest architecture. Galaxy clusters are the universe's grand metropolis's colossal gatherings where thousands of galaxies huddle together, bound by gravity's unrelenting pull. Picture a sprawling city at night, its light stretching as far as the eye can see, but on a scale so vast it defies comprehension. These clusters aren't just random assemblies, they're intricate networks with smaller groups of galaxies nested like neighborhoods within larger superclusters, forming a cosmic fractal that repeats across unimaginable distances. The Virgo cluster, our local example, contains over 1,000 galaxies, each an island of stars, yet it's just one modest node in the even greater Laniakea supercluster, a structure so enormous it dwarfs our Milky Way like a single grain of sand on a beach. What's truly mesmerizing is how these megastructures reveal the invisible hand of dark matter. When galaxy clusters collide, as in the famous Bullet cluster, the ordinary gas between galaxies smashes together, heating up and glowing in X-rays. But the galaxies themselves, along with the unseen dark matter, pass through almost unscathed, like ghosts slipping through walls. By mapping the gravitational lensing effects, the way these collisions bend light from background objects, astronomers can trace the dark matter's distribution, creating a shadowy blueprint of the cosmos's hidden scaffolding. These collisions are cosmic accidents that expose the universe's deepest secrets, showing us where the true mass lies, even when it refuses to shine. Yet the voids between these clusters are just as fascinating. Imagine a sponge, its holes stretching vast and empty, while the material around them clusters tightly. The universe is structured the same way, a cosmic web where galaxy clusters trace the dense filaments, and the voids between them span hundreds of millions of light years of near nothingness. These aren't just empty spaces, they're active players in the universe's expansion. Dark energy, the mysterious force accelerating the cosmos's growth, works most conspicuously here, pushing these voids apart like bubbles in an inflating loaf of bread. Some voids are so devoid of matter that light passing through them loses a tiny fraction of its energy, a redshift effect that serves as a fingerprint of the universe's accelerating expansion. The hierarchy of these structures, from lone galaxies to clusters to superclusters, mirrors the universe's self-organizing principles. Gravity pulls matter into denser knots, while dark energy stretches the fabric of space, creating a dynamic tension that shapes everything we see. It's a balance so delicate that slight changes in the early universe's density fluctuations determined where galaxies would bloom and where voids would yawn wide. Simulations of cosmic evolution, like the Illustris TNG project, recreate this process with stunning accuracy, showing how tiny quantum ripples in the newborn cosmos grew over billions of years into the web we observe today. And then there's the question of what lies beyond. If we could step back far enough, would these superclusters themselves form patterns within even larger structures? Some astronomers speculate that the universe might be fractal all the way up, with no fundamental limit to its clustering scale. Others argue that at some point, the expansion driven by dark energy would overwhelm gravity's pull, leaving superclusters as the final, isolated islands in an ever-cooling cosmos. Either way, these megastructures aren't just static landmarks, they're dynamic, evolving entities, their fates intertwined with the universe's ultimate destiny. So the next time you gaze at the night sky, remember, every pinpoint of light is part of a vaster architecture, a design written in gravity, dark matter, and the echoes of the Big Bang itself. Cosmic voids are the universe's silent giants, immense, almost empty regions where galaxies are vanishingly rare. Picture bubbles in a block of Swiss cheese, each hollow stretching hundreds of millions of light years across, their walls lined with the faint glow of distant galaxy clusters. The Boötes void is one of the most striking examples, a spherical desert of space so vast you could fit thousands of Milky Ways inside with room to spare. Yet despite their emptiness, these voids aren't passive. They're dynamic players in cosmic evolution, their expansion driven by dark energy's mysterious push. As these voids grow, they tug at the surrounding galaxies, subtly reshaping the large-scale structure of the universe. What's fascinating is how these voids form in the first place. In the early universe, tiny density fluctuations, slightly denser or sparser patches of matter, were imprinted by quantum ripples during the Big Bang. Over billions of years, gravity amplified these differences. Dense regions collapsed into galaxy clusters, while the emptier regions stretched and emptied further, like valleys deepening between mountain ranges. The result is a foamy, almost fractal-like architecture, where voids occupy most of the universe's volume, yet contain almost none of its mass. Some voids, like the one in the constellation Eridanus, are so devoid of matter that they act as cosmic cold spots in the microwave background, their emptiness subtly cooling light that passes through them. But here's the twist: voids aren't completely empty. Floating within them are a handful of rebel galaxies, isolated worlds that somehow got left behind. These loners, like the galaxy MCG plus 0102 in the Boötes void, challenge our understanding of how galaxies form. Without the usual density of neighbors to influence their growth, they evolve in unusual ways, their star formation rates and shapes differing from galaxies in crowded clusters. Studying these outliers helps astronomers untangle nature versus nurture in galactic evolution, whether a galaxy's fate is dictated by its environment or its inherent properties. Now shift your gaze from these vast emptiness to a pattern much closer to home, the Zodiac. For millennia, humans have looked to the stars and traced shapes among them, seeing not just randomness but symmetry and meaning. The 12 constellations of the Zodiac form a celestial belt encircling Earth's orbit, each one marking the sun's path through the sky over the course of a year. Ancient cultures from Babylon to Greece mapped these constellations, aligning them with seasonal changes and human affairs. But what's often overlooked is the precision behind this symmetry. The Zodiac isn't just a cultural artifact, it's a reflection of Earth's place in space, a geometric alignment that reveals our planet's tilt, orbit, and even the subtle wobble of its axis over millennia. The Zodiac's constellations appear to shift over time due to precession, a slow gyration of Earth's axis that completes a full cycle every 26,000 years. This means the stars that once marked the spring equinox in ancient Babylon no longer align with the same dates today. Yet despite this drift, the underlying symmetry remains. The Zodiac is a cosmic clock, its gears turning with celestial precision, each constellation a marker in humanity's eternal quest to find order in the heavens. Whether as a tool for navigation, a template for mythology, or a subject of scientific study, the Zodiac bridges the gap between human imagination and the universe's hidden geometry, a reminder that even in the chaos of space, patterns endure. The Zodiac isn't just a collection of star patterns, it's humanity's oldest celestial calendar, a grand clockwork mechanism written in the night sky. Picture standing beneath the stars 3,000 years ago, watching as the sun's path shifted slightly each month against a backdrop of constellations. To ancient Babylonians, this wasn't abstract astronomy. It was their agricultural planner, their religious guide, their way of marking the passage of seasons long before written calendars existed. They noticed how the sun's position among these star groups coincided with floods, harvests, and migrations, creating the first zodiac to track time itself. What's remarkable is how this system reveals Earth's motion in space. As our planet orbits the sun, our perspective shifts, making the sun appear to slide along a path called the ecliptic rite through the 12 constellations of the Zodiac. This creates an illusion of symmetry so perfect it feels intentional, like cosmic clockwork. But here's where it gets fascinating. That symmetry is slowly unraveling. Earth wobbles on its axis like a spinning top over a cycle of 26,000 years, a phenomenon called precession. This means the zodiac constellations gradually drift out of alignment with their original dates. So while Babylonian astrologers saw the sun in Aries during spring equinox, today it's actually in Pisces. This celestial drift didn't go unnoticed by ancient astronomers. The Greek astronomer Hipparchus detected precession in the 2nd century BC by comparing his star charts with Babylonian records centuries older. Imagine realizing the entire sky was subtly shifting beneath your feet, a discovery that must have felt both exhilarating and unsettling. Cultures worldwide built this knowledge into their monuments. Stonehenge's alignment with solstice sunrises, the Mayan observatory at Chichen Itza, even the Egyptian temples oriented to Sirius, all reflect an understanding that the heavens move in predictable, if slowly changing, cycles. Now consider eclipses, nature's most dramatic confirmation of the zodiac's geometry. When the moon crosses the ecliptic during a new or full moon, we get solar or lunar eclipses. Ancient astronomers from China to Mesopotamia tracked these events meticulously, recognizing they only occurred when sun, moon, and earth aligned along this zodiacal highway. The Babylonians developed the first eclipse prediction systems using their 19-year metonic cycle, while Greek astronomers like Ptolemy mapped the moon's inclined orbit relative to the ecliptic with astonishing precision. Modern astronomy reveals an even deeper layer to this celestial dance. The zodiac constellations aren't evenly spaced. Some, like Virgo, sprawl across large swaths of sky, while others, like Cancer, occupy much narrower segments. This irregularity exposes the zodiac as a human construct, a cultural lens through which we've projected order onto randomness. Yet its enduring power lies in how it connects us to generations past who likewise looked up and sought meaning in the stars' slow waltz. Whether as farmers tracking seasons or sailors navigating by starlight, humanity has always used these patterns to find our place in the cosmos, and that legacy continues every time we glance at a horoscope or marvel at an eclipse. The next time you see the moon glide past Jupiter or Saturn along the ecliptic, you're witnessing the same celestial geometry that guided ancient civilizations. It's a reminder that the universe's most profound designs aren't just in distant galaxies or quantum particles. They're written in the night sky above us, waiting to be read by anyone who takes the time to look. Solar and lunar eclipses are the universe's most dramatic demonstrations of celestial choreography, a fleeting moment when the sun, moon, and earth align with such precision that day turns to night, or the moon glows blood red. Think about the sheer improbability. The moon is 400 times smaller than the sun, but it's also 400 times closer, making their disks appear almost identical in size from our vantage point. This cosmic quirk is what creates the jaw-dropping spectacle of a total solar eclipse, where the moon perfectly blocks the sun's face, leaving only its shimmering corona visible. But this balance is temporary. The moon inches away from Earth at about 3.8 centimeters per year, meaning in roughly 600 million years, total solar eclipses will vanish from our skies forever. Eclipses have been more than just celestial events, they've rewritten history. In 490 BCE, a solar eclipse halted a battle between the Lydians and Medes, shocking both armies into peace. Centuries later, the same phenomenon helped Einstein prove his theory of general relativity when starlight bent around the sun during totality, just as he'd predicted. Even today, eclipses serve as cosmic laboratories, allowing scientists to study the sun's outer atmosphere or measure Earth's rotation slowing by milliseconds. But beyond their scientific value, there's something primal about standing in the moon's shadow, feeling the temperature drop and animals fall silent, a reminder that we're part of a vast, interconnected system. Now, shift your gaze from these grand alignments to the streaks of light that occasionally paint the night meteor showers. These aren't random sparks but the debris of comets, lingering like breadcrumbs along their orbital path. Every year, as Earth plows through these trails, particles no larger than grains of sand burn up in our atmosphere, creating fleeting streaks of light. The Perseids in August or the Geminids in December might seem chaotic, but their timing is as predictable as clockwork. That's because they're tied to Earth's orbit, intersecting with specific comet remnants. The Leonids, for example, originate from Comet Tempel-Tuttle, which swings by every 33 years, leaving a fresh trail of dust. What's mesmerizing is how these showers reveal invisible structures in space. The particles that create meteors are often arranged in filaments or clumps, tracing the gravitational currents of our solar system. By mapping meteor showers, astronomers can reconstruct the orbits of long-gone comets or even discover new ones. Some showers, like the quadrantids, are so narrow that Earth passes through them in just a few hours, a precision that hints at the delicate dynamics governing our cosmic neighborhood. And occasionally, we're treated to storms like the 1,833 Leonids, when thousands of meteors fell per hour, a spectacle so intense it sparked religious revivals and early scientific studies of meteors' origins. These celestial performances are more than just pretty lights. They're reminders of how dynamic our solar system truly is. Comets shed material, planets sweep through it, and for a brief moment we get to witness the aftermath. Whether it's the moon's shadow racing across continents or a flurry of meteors igniting the atmosphere, these events connect us to the rhythms of the cosmos, patterns etched in motion over millennia. And as we look up, we're not just spectators, we're participants, standing on a planet that's part of the dance. Meteor showers transform the night sky into a celestial fireworks display, but behind their fleeting beauty lies an intricate dance of gravity and debris. Every shower, from the Perseids' summer spectacle to the Geminids' winter glow, traces back to a cosmic breadcrumb trail, the dusty remnants of comets or, in rare cases, asteroids. As these parent bodies orbit the sun, they shed particles like pebbles dropped along a path, leaving behind streams of material no larger than grains of sand. When Earth's orbit intersects one of these trails, the particles collide with our atmosphere at staggering speeds, some exceeding 200,000 kilometers per hour, vaporizing in flashes of light we call meteors. The magic isn't just in their glow, but in their predictability. Take the Leonids, which peak every November. These meteors originate from Comet Tempel-Tuttle, a celestial traveler that completes its orbit every 33 years. Each return replenishes the debris field, creating denser trails that sometimes produce meteor storms, like the legendary 1833 event when thousands of meteors streaked across the sky every hour. Ancient records from China to Mesopotamia describe such storms with awe, often interpreting them as divine messages. Even today, their regularity serves as a celestial clock, helping astronomers map the solar system's invisible debris highways. What's astonishing is how these showers reveal hidden structures in space. The particles aren't scattered randomly, they cluster in filaments and knots, shaped by gravitational nudges from planets over centuries. The quadrantids, for example, produce a brief but intense burst each January because Earth slices through a narrow, concentrated stream. Meanwhile, the Eta Aquariids may spread across weeks, their broader trail reflecting the gradual dispersal of debris from Halley's Comet. By studying these patterns, scientists can reconstruct the orbits of long-lost comets or even predict future meteor storms decades in advance. Now, imagine a place where gravity and motion balance perfectly, where cosmic debris can accumulate without drifting away. These are Lagrange points, the solar system's parking spots, where the gravitational pull of two large bodies like the Sun and Earth cancels out the orbital motion of a smaller object. At these points, dust and rocks gather like leaves in a calm eddy, creating reservoirs of material that might someday fuel new meteor showers. The James Webb Space Telescope orbits at Lagrange point L2, 1 million miles from Earth, because this equilibrium minimizes fuel need. But these zones aren't just useful for spacecraft, they're cosmic crossroads where the universe's hidden architecture becomes visible. At L4 and L5, 60 degrees ahead and behind Earth in its orbit, scientists have detected clouds of dust trapped in gravitational harmony. Some theorize these could be the birthplaces of future meteor showers, as subtle tugs eventually nudge particles into Earth's path. Other Lagrange points, like those near Jupiter, host entire families of asteroids called Trojans, which have followed the gas giant for billions of years. These stable zones are like gravitational art galleries, preserving relics from the solar system's formation. What makes Lagrange points so fascinating is their duality. They're both anchors and accelerators. While they collect debris, they can also slingshot it outward when disturbances alter the balance. A passing star's gravity or the pressure of sunlight might one day dislodge these trapped particles, sending them spiraling toward Earth as a brand new meteor shower. It's a reminder that even the most stable corners of space are part of a dynamic, ever-changing system. So the next time you watch a meteor streak across the sky, remember, you're witnessing not just a burning speck of dust, but a fragment of a far grander celestial mechanism, one that connects comets, planets, and the silent gravitational symphonies of Lagrange points. Lagrange points are like cosmic parking spots, places where gravity and motion cancel each other out, creating pockets of perfect equilibrium. Picture a marble balanced precisely at the bottom of a bowl. Any slight nudge, and it rolls, but in these celestial sweet spots, objects can hover almost motionless relative to larger bodies. The James Webb Space Telescope orbits at L2, a Lagrange point about 1.5 million kilometers beyond Earth, because this position offers unparalleled stability. Here, the combined gravitational pull of Earth and the Sun counteracts the telescope's orbital motion, allowing it to maintain a fixed alignment with minimal fuel consumption. It's as if the universe carved out these zones specifically for observation, shielding spacecraft from the chaotic tugs of planetary orbits. But these points aren't just useful for telescopes, they're gateways for deeper exploration. Take Artemis, NASA's lunar mission, which plans to use the Earth-Moon L1 point as a staging ground for astronauts. This region, where Earth's and the Moon's gravity balance, could serve as a pit stop for spacecraft en route to the lunar surface or even Mars. Future space colonies might one day harness L4 and L5, the stable points 60 degrees ahead and behind the Moon in its orbit. These zones could become interplanetary hubs where supply depots or habitats float effortlessly, requiring little energy to maintain position. Imagine a bustling way station in the void, a crossroads for humanity's expansion into the solar system. Yet Lagrange points aren't just human inventions, they're natural phenomena with cosmic consequences. At L4 and L5, astronomers have found clouds of dust and even asteroids trapped in gravitational harmony. Jupiter's Trojan asteroids, for instance, cluster at its L4 and L5 points, remnants of the early solar system that have followed the gas giant for billions of years. These regions act like cosmic museums, preserving ancient material untouched by planetary collisions or solar winds. Some scientists speculate that similar dust clouds near Earth's Lagrange points might one day seed new meteor showers if disturbances send particles spiraling into our atmosphere. What makes these points so fascinating is their duality. They're both anchors and launch pads. While they collect debris, they can also slingshot objects outward when the balance shifts. Solar radiation pressure or the gravity of a passing star might nudge trapped material, sending it careening into new orbits. This delicate dance reveals the hidden architecture of space, where gravity's invisible threads weave a framework that shapes everything from spacecraft trajectories to the birth of comets. Now, shift your gaze from these silent gravitational hubs to one of the universe's most explosive mysteries: fast radio bursts. These fleeting blasts of energy, lasting just milliseconds, pack the power of hundreds of millions of suns, yet their origins remain shrouded in cosmic intrigue. Fast radio bursts are like the universe's most cryptic text messages, blasts of energy so powerful they outshine entire galaxies for a fraction of a second, then vanish without a trace. These millisecond flashes of radio waves travel billions of light years to reach us, carrying signatures of the cosmic highways they've traversed. Some burst once and never repeat, like cosmic fireworks that leave astronomers scrambling to catch them before they fade. Others, like FRB 121102, flicker on and off at irregular intervals, as if teasing us with glimpses of a pattern we can't quite decipher. When scientists analyzed these signals, they noticed something peculiar. The waves arrived stretched out, with higher frequencies reaching Earth before lower ones. This dispersion measure isn't random noise. It's a fingerprint of the intergalactic medium, revealing how much material these bursts punched through on their journey. The leading theories about what causes FRBs read like a sci-fi anthology. One points to magnetars, highly magnetized neutron stars that occasionally unleash starquakes, vibrating their magnetic fields like plucked guitar strings and releasing torrents of radio waves. Another suggests collisions between neutron stars or black holes, cataclysmic mergers that send shockwaves rippling through spacetime. Then there's the wild card: could some FRBs be artificial? While most astronomers dismiss extraterrestrial origins, the possibility lingers in the background, a reminder of how little we truly understand. The repeating bursts, with their irregular but non-random cadence, particularly spark curiosity. If natural, what cosmic engine could produce such sporadic yet structured signals? If not, well, that's a conversation for another day. What's undeniable is how FRBs illuminate the invisible scaffolding of the universe. As these radio waves traverse galaxies and intergalactic voids, they interact with free-floating electrons, slowing down slightly in a way that depends on their frequency. By measuring this dispersion, astronomers can map the distribution of matter across cosmic distances, like using a flashlight beam to gauge the thickness of fog. Some FRBs even exhibit scattering, where their signals smear out as they pass through turbulent plasma near galaxies. This isn't just interference, it's a treasure trove of data about the environments these bursts have traveled through, from the halos of distant galaxies to the filaments of the cosmic web. Now shift your gaze from these enigmatic flashes to a celestial structure where symmetry reigns supreme: planetary rings. While FRBs hint at chaos and mystery, rings like Saturn's showcase the universe's flair for precision. These dazzling bands of ice and rock aren't haphazard debris fields. They're sculpted by gravity into razor-sharp edges and intricate gaps. The Cassini division, that striking dark band in Saturn's rings, exists because of a gravitational resonance with the moon Mimas. For every 2 orbits a ring particle completes, Mimas completes one, tugging persistently until a void forms. Similar resonances create the Keeler gap, where the tiny moon Daphne's weaves ripples through the ring material like a boat's wake. The symmetry of rings extends beyond Saturn. Jupiter's faint rings, Uranus's dark bands, even the razor-thin rings of Neptune, all bear the marks of gravitational choreography. Some rings contain shepherd moons, whose gravity herds particles into narrow strands, while others spiral outward in patterns resembling phonograph records. These structures aren't static. They're dynamic systems where particles collide, coalesce, and spiral inward over millennia. The same physics that arranges a child's toys in a spinning merry-go-round, with heavier objects drifting outward and lighter ones staying near the center, shapes these cosmic disks on a scale that dwarfs our solar system. What ties FRBs and planetary rings together is their ability to reveal hidden forces. One does it through fleeting, energetic chaos, the other through patient, gravitational order. Both serve as cosmic messengers, one carrying tales of distant violence, the other whispering the quiet laws of motion. And both remind us that the universe speaks in patterns, whether written in radio static or the glittering arcs of a ringed planet. Saturn's rings might be the crown jewels of our solar system, but they're far from alone in this celestial jewelry box. Jupiter's faint, dusty halos, Uranus's dark and narrow bands, even Neptune's delicate arcs. Each system tells a story of gravity's artistry. These rings aren't solid hoops, they're shimmering rivers of ice, rock, and dust, where every particle follows its own precise orbit like a car on a cosmic freeway. The sheer scale is staggering. Saturn's main rings stretch over 280,000 kilometers wide, yet some are barely 10 meters thick, a sheet of paper compared to a football field. What makes these structures so mesmerizing isn't just their beauty but their precision. Take the Cassini division, that striking dark gap in Saturn's rings. It's not empty space, it's a gravitational echo carved out by the moon Mimas. Every time a ring particle completes 2 orbits, Mimas completes one, tugging persistently until particles are nudged away, leaving a void. This phenomenon, called orbital resonance, is nature's metronome, creating rhythms that sculpt the rings into intricate patterns. The Keeler Gap, another razor-thin divide, owes its existence to the tiny moon Daphnes, whose gravity ripples the surrounding material like a stone dropped in a pond. Even the seemingly chaotic spokes' dark radial streaks that appear and vanish are now thought to be levitated dust influenced by Saturn's magnetic field. But why do only some planets have rings? The answer lies in a delicate cosmic recipe. Rings form when debris, shattered moons, captured comets, or leftover planetary building blocks gets trapped close to a planet. Too far and the pieces drift away, too close and they crash into the atmosphere. Gas giants like Saturn have a sweet spot. Their strong gravity captures debris, while their many moons shepherd the material into neat bands. Smaller, rocky worlds lack the gravitational pull to maintain such structures. Mars's 2 tiny moons might one day crumble into rings, while Earth's moon is too distant and stable to suffer that fate. Uranus offers a fascinating twist. Its rings are dark as charcoal and tilted sideways, likely the remnants of a cataclysmic collision that knocked the planet onto its side. Neptune's arcs, meanwhile, are mysteriously clumped, held together by the gravitational influence of the moon Galatea. Even Jupiter's faint rings, made mostly of dust kicked up by meteoroid impacts on its inner moons, reveal how dynamic these systems are, constantly replenished, eroded, and reshaped. Now, shift your gaze beyond the glow of planetary rings to the invisible architecture that shapes entire galaxies' dark matter halos. These ghostly structures, far larger than any ring system, dictate the fate of cosmic neighborhoods through gravity alone. Dark matter halos are the universe's hidden architects, vast, invisible structures that cradle galaxies like ghostly hands shaping cosmic clay. Though we can't see them directly, their gravitational fingerprints are everywhere. Picture a galaxy like our Milky Way not as an island floating in emptiness, but as the glittering core of a colossal, unseen sphere, a halo of dark matter stretching 10 times farther than the galaxy's visible edge. This phantom framework doesn't just sit idly by, it actively molds the universe, determining how galaxies spin, cluster, and even collide. The strange thing about these halos is how they're structured. Unlike a smooth cloud, they have a distinct gradient, denser toward the center, wispier at the edges like an ethereal onion with layers of varying intensity. Computer simulations reveal even more complexity. Within each halo, smaller clumps of dark matter orbit like submerged icebergs, remnants of smaller galaxies consumed long ago. These subhalos trace intricate filaments, forming a cosmic web within a web. When astronomers study the rotation of spiral galaxies, they find stars at the outer edges moving just as fast as those near the core, a phenomenon that defies Newtonian physics unless some unseen mass, some dark matter halo, is providing extra gravitational pull. Now zoom out to an even grander scale. These halos don't exist in isolation, they cluster, forming nodes where galaxies gather like fireflies caught in invisible nets. This brings us to one of the universe's great mysteries, the Great Attractor. Located some 250 million light-years away, this gravitational anomaly pulls entire galaxies, including our own Milky Way, toward it at staggering speeds. At first, astronomers thought it might be a massive collection of visible matter, a supercluster of galaxies. But when they looked, they found only scattered galaxies, nowhere near enough to account for the pull. The true source, an immense concentration of dark matter halos, their combined gravity bending the flow of the cosmos like a hidden whirlpool in space. Mapping these halos could revolutionize our understanding of dark matter itself by studying how they warp light from background galaxies, a phenomenon called gravitational lensing. Scientists have begun charting their distribution. Some theories suggest dark matter might interact weakly with itself, creating subtle density waves within halos. Others propose it could decay over eons, leaving faint energy signatures. The more we learn about these invisible scaffolds, the closer we get to answering the ultimate question: what is dark matter made of? Is it a new fundamental particle, a shadowy twin to the atoms we know? Or does it hint at deeper flaws in our theories of gravity? One thing is certain: without dark matter halos, galaxies as we know them wouldn't exist. They provide the gravitational wells where gas can cool and condense, birthing stars and planets. When galaxies collide, it's often their dark matter halos that first engage in a slow cosmic waltz, dictating the eventual merger of their luminous counterparts. In this way, these unseen structures don't just shape the universe, they write its history, silently guiding the evolution of everything we can see. So the next time you gaze at a spiral galaxy's graceful arms, remember, what truly holds them together is far more mysterious and far more magnificent than meets the eye. The Great Attractor lurks in the cosmic shadows like a gravitational siren, pulling thousands of galaxies, including our own Milky Way, toward some unseen destiny. Imagine the entire local group of galaxies, 100 trillion stars strong, drifting through space at over 2 million kilometers per hour toward a point we can't even see, obscured by the dusty veil of our galaxy's central bulge. This mysterious region, centered in the constellation Norma, exerts a pull so immense it challenges everything we know about the distribution of matter in the universe. Early observations in the 1970s revealed something peculiar. Galaxies weren't just expanding outward from the Big Bang, they were streaming in a specific direction, as if drawn by some colossal, hidden magnet. What makes this anomaly so baffling is the mismatch between what we observe and what we expect. When astronomers first calculated the mass needed to produce such a gravitational tug, they pointed their telescopes toward the suspected region, only to find far fewer galaxies than required. The visible matter there, including the Norma cluster, accounts for less than 10% of the necessary mass. So where's the rest? The leading theory points to dark matter, an invisible scaffold of particles weaving through the cosmos, its gravity sculpting the motions of galaxies like an unseen hand. But even accounting for dark matter, the Great Attractor's pull seems too strong, hinting at something even grander at play. Some cosmologists propose it's not a single structure but a confluence of forces, a river of galaxies flowing toward an even more massive supercluster called the Shapley Attractor, over 600 million light-years away. Others wonder if the Great Attractor is just one visible piece of a larger pattern, a ripple in the cosmic web where dark matter filaments converge like highways meeting at a bustling interchange. The most startling possibility, that we're seeing the fingerprints of primordial quantum fluctuations, microscopic wrinkles from the universe's first moments stretched to cosmic proportions by inflation, now dictating the flow of entire galactic superclusters. Yet for all its mystery, the Great Attractor isn't pulling us toward doom. The expansion of the universe ensures we'll never actually reach it. Dark energy's relentless push will eventually overpower even this colossal gravitational whisper. But its existence reminds us how much remains hidden in plain sight. Every time astronomers peer through the Milky Way's dusty curtain with infrared and radio telescopes, they uncover new clusters, new filaments, new pieces of the puzzle. The Great Attractor isn't just a destination, it's a compass pointing toward deeper truths about the invisible architecture of the cosmos. Now, let's rewind to the universe's first moments when the seeds of such structures were sown. Cosmic inflation, the brief, explosive expansion that shaped the infant cosmos, holds the key to understanding how randomness birthed order and how quantum flickers became the blueprints for galaxies, clusters, and the Great Attractor itself. Cosmic inflation wasn't just an expansion, it was the universe's first and most dramatic act of creation, stretching space itself faster than light in a fraction of a second. Picture a speck smaller than an atom suddenly swelling to the size of a grapefruit, then continuing to grow exponentially. This wasn't the steady expansion we see today. It was a violent stretching of space-time, smoothing wrinkles and amplifying quantum fluctuations into cosmic blueprints. Those microscopic ripples, born from quantum uncertainty, became the seeds for everything: galaxies, clusters, even the vast cosmic web. Without inflation, the universe would lack the intricate structure we marvel at today. The evidence for this explosive growth is etched into the cosmic microwave background, that ancient afterglow from the Big Bang. Tiny temperature variations, hot and cold spots no larger than 1 part in 100,000 form a speckled pattern across the sky. These aren't random, they match predictions of inflation perfectly, showing how quantum jitters were stretched across the cosmos, frozen into the fabric of space-time. The European Space Agency's Planck satellite mapped these variations with astonishing precision, revealing a spectrum of fluctuations that align with inflationary models like a key fitting a lock. Even the slight preference for larger-scale patterns, a tilt in the data called the spectral index, hints at inflation's unique physics, where space didn't just expand but did so with a slight slowdown before ending. But inflation's implications stretch beyond what we can observe. If the theory holds, the universe we see is just a tiny bubble in an unfathomably larger multiverse. Imagine a frothing sea of spacetime where countless inflationary regions bubble up, each with its own laws of physics. Some might collapse instantly, others could spawn entirely new universes. Our cosmos, with its finely tuned constants allowing for stars and life, might be one rare pocket where conditions align just right. This idea, eternal inflation, suggests that the patterns we see in our universe are just local brushstrokes on an infinite canvas. The holographic principle takes this even further, proposing that all the information in our three-dimensional universe could be encoded on a two-dimensional surface at its boundary. Think of it like a cosmic credit card hologram, where a flat surface contains all the data needed to reconstruct a three-dimensional image. In this view, the universe's complexity isn't just shaped by inflation, it's projected from a deeper, more fundamental layer of reality. Black holes already hint at this. Their entropy or information content scales with their surface area, not their volume. If the entire universe operates similarly, then the intricate designs we see, from galaxy clusters to quantum particles, might be shadows of a simpler, hidden order. What's staggering is how these ideas connect the unimaginably large to the infinitesimally small. Inflation's quantum fluctuations, amplified to cosmic scales, gave rise to galaxies. The holographic principle suggests those galaxies might be projections of information stored at the universe's edge. Together, they paint a picture of a cosmos far stranger and more interconnected than we ever imagined, one where patterns repeat across scales, from the quantum foam to the cosmic web, all tracing back to those first fleeting moments of exponential expansion. The holographic principle turns our understanding of reality inside out. What if the three-dimensional universe we perceive is just a projection, a cosmic illusion painted on a two-dimensional surface at the edge of space? Think of it like a movie theater screen. The images appear to have depth, but every detail is encoded in flat pixels. This mind-bending idea didn't come from science fiction. It emerged from the study of black holes, where physicists like Jacob Bekenstein and Leonard Susskind realized something startling. The information swallowed by a black hole isn't lost. It's imprinted on the event horizon, the point of no return, like a holographic film storing a 3D image. But why would the entire universe work this way? The math suggests an astonishing possibility. The fabric of spacetime might not be fundamental. Instead, it could be a secondary layer, projected from a deeper reality where information is stored on a vast, unseen boundary. Imagine the universe as a giant black hole. Every event, every particle, every galaxy could be pixels on its spherical surface, translated into the 3D world we experience. This isn't just abstract theorizing. When scientists calculate the maximum entropy, the information capacity of any region of space, it scales with the area of its boundary, not its volume. That's like saying the data in a room depends on the wall's surface area, not the space inside. If the holographic principle holds, it could explain some of the universe's most puzzling symmetries. The fractal patterns in galaxy clusters, the repeating ratios in orbital resonances, even the way quantum particles entangle across distances, all might be shadows of a simpler, lower-dimensional code. String theory, which attempts to unify all fundamental forces, finds elegant solutions in holographic models where higher dimensional physics emerges from interactions on a boundary. Even the cosmic microwave background's fluctuations, those faint echoes of the Big Bang, might carry hints of this underlying structure. Now, shift your gaze from the abstract to the breathtakingly concrete. The Fibonacci sequence, a mathematical rhythm that echoes through the cosmos. From the spiral arms of galaxies to the arrangement of sunflower seeds, this pattern appears with uncanny frequency. The sequence starts simply 0, 1, 1, 2, 3, 5, 8, each number the sum of the two before it. But when you plot these ratios, something magical happens. The numbers converge to the golden ratio, approximately 1.618, a proportion revered by artists and architects for its aesthetic harmony. In nature, this ratio minimizes wasted space and maximizes efficiency. The Milky Way's spiral arms, for instance, unfurl in a logarithmic spiral that adheres closely to the Fibonacci sequence. Each turn of the spiral grows wider by the golden ratio, creating a structure that's both sturdy and adaptable. The same pattern appears in hurricanes, in the curl of ocean waves, even in the branching of trees, a universal blueprint for growth and resilience. What's mesmerizing is how these mathematical threads weave through scales. The DNA molecule, the blueprint of life, twists in a double helix with a rotation every 10 base pairs, a ratio suspiciously close to the golden mean. Distant galaxies like M74 showcase near-perfect Fibonacci spirals, their stars tracing curves that mirror the chambers of a Nautilus shell. Even time itself might follow this rhythm. Some physicists speculate that quantum fluctuations in the early universe could have been governed by Fibonacci-like sequences, planting the seeds for large-scale cosmic structures. So here's the tantalizing question. Are these patterns mere coincidence, or do they hint at something deeper? Could the holographic principle and the Fibonacci sequence be two sides of the same cosmic coin, one revealing the universe's hidden code, the other its visible artistry? As we peel back the layers of reality, from black hole thermodynamics to spiral galaxies, we're left with a profound sense of connection. The universe isn't just random, it's a masterpiece written in geometry, waiting for us to decipher its language. Galactic spirals seem to dance to a mathematical rhythm written into the fabric of the universe itself. Take the Whirlpool Galaxy, its arms swirling outward in a near-perfect logarithmic spiral, each curve growing wider by a factor of roughly 1.618, the golden ratio. This same number appears in the seed arrangement of sunflowers, the curve of nautilus shells, even the branching of human lungs. The Fibonacci sequence, where each number is the sum of the two before it, generates this ratio naturally as it unfolds. But what's astonishing is how this earthly math echoes across cosmic scales. In galaxies like M74, star-forming regions cluster along spiral arms at intervals that mirror Fibonacci spacing, as if the universe adheres to a universal growth algorithm. The secret may lie in density waves, ripples of compressed gas that orbit galaxies slower than their stars. As stars and gas move through these waves, they pile up like cars in a traffic jam, creating the bright spiral arms we see. This process doesn't just produce random swirls, it favors patterns that balance gravitational stability with efficient growth. The golden ratio's spiral minimizes shear forces, allowing arms to persist for billions of years without winding too tight or unraveling. It's nature's way of optimizing space, just as sunflowers pack seeds tightly or hurricanes organize into spirals to conserve energy. Yet the cosmic web takes this geometry even further. Filaments of dark matter threading the universe often branch at angles close to the golden ratio, connecting galaxy clusters in a fractal-like network. Simulations of cosmic evolution show how slight density variations in the early universe grew into this web, with knots and threads forming at scales that echo Fibonacci-like hierarchies. Some researchers speculate that quantum fluctuations during inflation, the universe's explosive infancy, might have followed mathematical sequences that later imprinted on galactic structures. But is this more than coincidence? Skeptics argue that with infinite galaxies, some are bound to match earthly patterns by chance. Yet when the same ratios emerge in atomic orbitals, planetary orbits, and galaxy clusters, it's hard to dismiss as mere accident. Perhaps the universe isn't just governed by laws, it's shaped by mathematical harmonies that transcend scale, a symphony where Fibonacci numbers are the recurring refrain. Now shift your gaze from galactic spirals to the voids between them, where the cosmic web's geometry takes on an even grander form. These vast, empty regions aren't random gaps. They're sculpted by dark energy and gravity into polyhedral shapes, their edges tracing the golden ratio in 3 dimensions. The universe, it seems, paints with the same brushstroke, whether crafting a seashell or a supercluster. The cosmic web isn't just a random tangle of galaxies, it's a meticulously structured network, a labyrinth of light and dark matter woven into a geometric masterpiece. Picture the branching veins of a leaf or the interconnected neurons of a brain, then magnify that pattern to span so vast they dwarf entire superclusters. This colossal architecture is built from 3 fundamental elements: dense knots where galaxies swarm like fireflies, thread-like filaments connecting them, and vast, empty voids between. What's astonishing isn't just the scale, but the precision, the way these components obey mathematical scaling laws. Their sizes and distributions following ratios seen everywhere from snowflakes to stock markets. At the heart of this design lies dark matter, the universe's invisible sculptor. From tiny quantum ripples in the fiery aftermath of the Big Bang, gravity amplified minuscule density variations over billions of years, pulling matter into a web of filaments and nodes. Supercomputer simulations like Illustris TNG recreate this evolution with eerie accuracy. showing how dark matter's gravitational tendrils guided ordinary matter into the glowing galaxies we observe. The resulting structure isn't chaotic. It's a fractal-like repetition where clusters nest within superclusters and filaments branch into ever smaller threads, echoing the same patterns across different scales. The resemblance to natural networks is uncanny. Slime molds, when searching for food, construct branching networks almost identical to the cosmic web's filaments. River deltas carve tributaries that mirror the universe's dark matter highways. Even the Internet's infrastructure evolves along similar lines. This isn't mere coincidence. It's a testament to universal principles of efficiency. Whether it's nutrients, data, or galaxies, nature favors pathways that minimize energy and maximize connectivity. Yet the cosmic web holds mysteries no earthly analog can explain. Why do voids, those immense, empty bubbles, tend toward polyhedral shapes, their flat surfaces meeting at precise angles? How do filaments maintain their delicate balance, resisting gravity's pull to collapse into knots? The answers might lie in dark energy, the enigmatic force accelerating the universe's expansion. As voids stretch, they press filaments into sharper geometric arrangements, like foam hardening into a honeycomb. Now stretch your imagination beyond our universe. If the cosmic web is a fractal, could it be just one thread in an even grander multiverse tapestry? Some theories suggest other universes might have webs with entirely different geometries, some sparse and ragged, others densely knotted. Their symmetries, dictated by alternate physics, could range from crystalline lattices to swirling helices. The very idea reshapes our understanding of reality. What we call the universe might be a single note in an infinite symphony of cosmic designs. Multiverse theory stretches the boundaries of imagination. What if our universe is just one page in an infinite cosmic library, each volume written with different physical laws? Among these countless possibilities, some universes might resemble ours in surprising ways, their structures echoing familiar symmetries. Picture a hall of mirrors where reflections aren't identical but variations on a theme. Some universes might have stronger gravity, others with fractured dimensions, yet a few could mirror our own cosmic web, their galaxies arranged in eerily similar patterns. The symmetry wouldn't be perfect, but the underlying mathematics might resonate like harmonies in a grand symphony. Barion acoustic oscillations offer a tantalizing clue. These are fossilized ripples in the distribution of galaxies, imprints of pressure waves that traveled through the early universe's hot plasma like sound, ringing through a bell. When the cosmos cooled enough for light to travel freely, these waves froze in place, leaving a subtle signature. Galaxies today are slightly more likely to be separated by about 500 million light-years, a cosmic yardstick etched into the universe's fabric. This pattern isn't random, it's a snapshot of the universe's infancy, a fingerprint of its initial conditions. Now, imagine this fingerprint repeating across multiverses. If inflation, the universe's explosive early expansion, occurred in cycles or bubbles, each new universe might carry traces of these oscillations, like siblings sharing genetic markers. Some theories suggest that in a multiverse, certain constants or structures could recur statistically, creating pockets where Barion acoustic oscillations appear in recognizable forms. It's as if the universe's blueprint has a preferred design, a template that emerges even when the materials change. The real mystery lies in what these patterns imply. If multiple universes exhibit similar large-scale structures, does that hint at a deeper, shared origin? Or is it simply that only universes with such symmetries can harbor galaxies, stars, and life, a selection bias we're unknowingly subject to? This idea, called the anthropic principle, suggests we observe these patterns because they're necessary for our existence. other universes might lack them entirely, their laws too chaotic or sterile to build complexity. Yet there's another possibility that these oscillations are threads connecting universes in a higher dimensional tapestry. String theory proposes that our universe could be a membrane floating in a higher dimensional space, occasionally colliding with others. Such collisions might leave imprints in the cosmic microwave background or subtly alter the distribution of galaxies. While evidence remains elusive, the mathematical elegance is compelling. What we perceive as random variations in galaxy clusters could be shadows of neighboring universes brushing against our own. What makes Barion acoustic oscillations so fascinating isn't just their regularity, it's their resilience. They've survived nearly 14 billion years of cosmic evolution, from the quark-gluon plasma of the Big Bang to the sprawling web of galaxies we see today. In a multiverse, such enduring patterns might be rare or commonplace, depending on the fundamental rules of each reality. By mapping them with telescopes like the Dark Energy Survey, we're not just studying our universe's history, we're potentially glimpsing the architecture of existence itself. So the next time you hear about the cosmic web's intricate design, remember, it might be more than a local phenomenon. Those filaments and voids could be stitches in a multiversal quilt, woven from threads of symmetry we're only beginning to trace. Whether echoes of sibling universes or artifacts of our unique cosmic recipe, these patterns remind us that the universe's beauty often lies in its repetitions and its mysteries. Barion acoustic oscillations are like cosmic fossils, imprints of sound waves that rippled through the newborn universe when it was a seething plasma of particles and light. Picture the early cosmos as a dense, hot soup where photons and baryons, protons and neutrons were locked in a relentless push and pull. Gravity tried to clump matter together, while radiation pressure from photons pushed it apart, creating oscillations that traveled outward like ripples in a pond. Then, around 380,000 years after the Big Bang, the universe cooled enough for atoms to form, freeing photons in what we now see as the cosmic microwave background. But those ripples didn't vanish. They froze in place, leaving a subtle pattern in the distribution of matter, a whisper of the universe's first vibrations. Today, this pattern lingers as a preference for galaxies to be separated by roughly 500 million light-years, a cosmic yardstick etched into the fabric of space. It's as if the universe left breadcrumbs for us to follow, a standardized scale against which we can measure its expansion. When astronomers map millions of galaxies in projects like the Sloan Digital Sky Survey, they don't see randomness. Instead, they find a faint but unmistakable clustering at this specific distance, like echoes of a drumbeat from the dawn of time. This isn't just a curiosity. It's one of our most powerful tools for probing dark energy, the mysterious force accelerating the universe's expansion. By tracking how this scale changes over cosmic time, scientists can gauge how dark energy's influence has evolved, testing whether it's a constant force or something stranger. What's astonishing is how resilient these oscillations are. Over billions of years, through galaxy collisions, supernova explosions, and the relentless pull of dark matter, that primordial fingerprint remains detectable. It's a testament to the universe's deep-seated order, a structure so fundamental that not even the chaos of cosmic evolution could erase it. Some theories suggest these patterns might even hold clues to physics beyond our current understanding. If dark energy behaves differently than we expect, or if gravity weakens on cosmic scales, the precise measurements of Barion acoustic oscillations could reveal these deviations like a crack in a mirror. Now, shift your focus from these vast, frozen ripples to the universe's most enigmatic shortcuts, wormholes. While Barion acoustic oscillations trace the universe's expansion, wormholes tease the possibility of bending space-time itself. Imagine folding a piece of paper so two distant points touch. A wormhole would be the tunnel piercing through that fold, connecting places that should be impossibly far apart. The math of general relativity allows for such structures, though no one has ever observed one. Theoretical models describe them as bridges with two mouths linked by a throat, potentially spanning not just space but time. The geometry of wormholes is as mesmerizing as it is speculative. Unlike black holes, which trap everything behind an event horizon, traversable wormholes, if they exist, would require exotic matter with negative energy to keep their throats open. Picture a tunnel lined with a substance that defies gravity, pushing outward to prevent collapse. Some solutions in string theory even suggest wormholes could be entangled quantum particles scaled up to cosmic proportions, where entering one mouth instantly transports you to its partner, no matter how far apart they are. While this sounds like science fiction, the equations hint that the universe's geometry might permit such wild possibilities. Yet wormholes aren't just cosmic party tricks. They could reshape our understanding of reality. If they exist, they'd challenge our notions of causality, allowing information or even matter to traverse vast distances faster than light. Some physicists speculate that wormholes might be hiding in plain sight, disguised as black holes, their true nature obscured by our limited vantage point. Others argue that quantum effects would inevitably destabilize them, snapping them shut before anything could pass through. But the mere fact that these structures emerge from our best theories of gravity suggests that space-time is far more malleable, far more mysterious than we ever imagined. Whether frozen echoes of sound waves or hypothetical tunnels through the cosmos, these phenomena reveal a universe that's not just expanding but intricately structured, a place where geometry writes the rules, and we're only beginning to learn its language. Wormholes aren't just science fiction, they're theoretical tunnels through the very fabric of space-time, shortcuts that could connect distant corners of the universe in the blink of an eye. Imagine crumpling a sheet of paper and poking a hole through two layers. That's the essence of a wormhole's geometry. But keeping these cosmic passageways stable is no small feat. According to Einstein's equations, a traversable wormhole would need exotic matter, a substance with negative energy density, to prop open its throat and prevent it from collapsing instantly. This isn't just hypothetical. Quantum physics allows for fleeting instances of negative energy, like the Casimir effect, where closely spaced metal plates create a tiny repulsive force in a vacuum. Could nature scale this phenomenon up to cosmic proportions? The search for wormhole signatures has led scientists to some surprising places. Gravitational wave detectors like LIGO might hold the key. If a wormhole's throat vibrates, perhaps from matter passing through, it could emit ripples in spacetime with a distinct frequency, like a bell ringing in the dark. Some models predict these waves would carry an echo, a faint secondary signal caused by the wormhole's unique geometry. In 2019, researchers analyzing LIGO data spotted an unusual repeating pattern in a gravitational wave event, sparking speculation about exotic origins. While the finding remains controversial, it underscores how the universe's hidden designs might reveal themselves in subtle, unexpected ways. Gamma-ray bursts, the most energetic explosion since the Big Bang, could also be wormhole calling cards. These fleeting flashes of high-energy light often come in pairs, separated by milliseconds. One theory suggests they might be the result of a wormhole's mouths snapping shut, releasing pent-up energy like a cosmic rubber band. Even more intriguing are bursts with oddly symmetric properties, their light curves mirroring each other with mathematical precision. Could these be the imprint of a wormhole structure, its two ends behaving like entangled quantum particles, instantly mirroring activity across vast distances? But the most mind-bending possibility is that wormholes aren't just spatial shortcuts, they could be time machines. A wormhole with one mouth moving near a black hole and the other remaining stationary would create a time difference between its ends, effectively forming a bridge to the past or future. The catch: building such a structure would require engineering on a galactic scale and materials that defy known physics. Yet the mere possibility hints at a universe where time itself might be more malleable than we ever imagined, its flow shaped by hidden geometries we've only begun to glimpse. Now shift your gaze from these theoretical tunnels to the violent, brilliant flashes of gamma-ray bursts, cosmic beacons that might carry clues to spacetime's deepest secrets. Gamma-ray bursts are the universe's ultimate fireworks, blinding flashes of energy so intense they outshine entire galaxies for a few fleeting seconds. These cosmic detonations release more power in milliseconds than our Sun will emit over its entire 10 billion-year lifetime. The numbers defy comprehension. A single GRB can discharge up to 10 to the 54 ergs of energy, equivalent to converting the entire mass of the Sun directly into gamma rays. Yet what makes these events truly fascinating isn't just their raw power. It's the intricate patterns hidden within their afterglows. When astronomers analyze the light curves of GRBs, they sometimes find unexpected repetitions, subtle dips and peaks in brightness that recur with mathematical precision, like cosmic Morse code blinking across the void. Take GRB 1211-2, one of the most studied bursts on record. Its afterglow didn't fade smoothly but showed distinct rebrightening events at precisely 25 and 150 days after the initial explosion. This wasn't random noise, it was a clue pointing to structured activity in the aftermath. Some theorists suggest these patterns could trace back to the central engine powering the burst, perhaps a newly formed magnetar, a neutron star with a magnetic field 1,000 trillion times stronger than Earth. As this stellar corpse spins wildly, its magnetic field might flicker like a lighthouse beam, creating periodic energy injections into the expanding shockwave. Other models propose that debris falling back onto the black hole formed during the explosion could produce quasi-periodic oscillations, similar to water dripping rhythmically into a pond. The leading theories split GRBs into two cosmic families. Long bursts lasting over 2 seconds often coincide with the violent deaths of massive stars in supernova. Picture a colossal sun 20 times heavier than our own, collapsing under its gravity as its core implodes into a black hole. Twin jets of plasma, hotter than 1 trillion suns, drill through the star's outer layers at nearly light speed before erupting into space, a collapsar model that explains the prolonged energy release. Short bursts lasting under 2 seconds tell a different story. These appear linked to neutron star mergers, where two ultra-dense stellar corpses spiral together in a final, fatal embrace. The 2017 detection of GRB 170817, accompanied by gravitational waves from such a merger, proved this connection beyond doubt. The kilonova explosion that followed produced enough gold and platinum to outweigh our entire planet, a dazzling byproduct of cosmic cataclysms. But here's the haunting question: could these bursts follow a deeper cosmic rhythm? Some astronomers have noted curious temporal clustering in GRB occurrences, with bursts appearing to align along large-scale structures in the universe. Others analyze their energy distributions, searching for harmonics that might hint at universal resonance. While no definitive pattern has emerged, the mere possibility reminds us how much we still don't understand about these staggering events. What we do know is that GRBs serve as cosmic lighthouses. Their light, traversing billions of light-years, carries imprints of the galaxies and intergalactic medium they've pierced. By decoding their spectra, we've discovered vast reservoirs of previously invisible gas in the early universe and probed the epoch when the first stars ignited. Now shift your gaze from these explosive beacons to something far more subtle yet equally profound, the Higgs field. While GRBs showcase the universe's raw power, the Higgs represents its delicate symmetry, an invisible energy field that permeates every corner of existence. This field isn't just theoretical, it's what gives particles their mass, shaping the very structure of reality. Without it, atoms wouldn't form, stars wouldn't shine, and life as we know it couldn't exist. The dance between these extremes, the violent brilliance of GRBs and the silent perfection of the Higgs, reveals a universe of breathtaking contrasts, where chaos and order intertwine in ways we're only beginning to fathom. The Higgs field is like an invisible cosmic molasses, pervading every corner of space and giving particles their mass through a process called symmetry breaking. Picture the early universe as a scorching, chaotic place where particles zipped around at light speed, massless and free. Then, as the cosmos cooled to 1 trillion degrees about a picosecond after the Big Bang, the Higgs field underwent a dramatic shift, like water freezing into ice. This phase transition broke the universe's perfect symmetry, and suddenly, particles moving through this field began to experience resistance. Some, like quarks and electrons, got bogged down, acquiring mass. Others, like photons, slipped through unaffected, remaining massless. This elegant mechanism explains why the building blocks of matter have weight while light does not, a fundamental mystery solved by a field we can't even see. The discovery of the Higgs boson in 2012 at CERN Large Hadron Collider was a triumph of modern physics, confirming a prediction made nearly 50 years earlier. Detecting this particle proved the Higgs field exists, completing the Standard Models puzzle. But here's the twist: the Higgs raises more questions than it answers. Its measured mass, 125 gigaelectronvolts, is suspiciously light compared to theoretical expectations. Without some balancing act, quantum fluctuations should have made it exponentially heavier, unless unknown particles or forces are at play. Some theorists propose supersymmetry, where every known particle has a heavier twin, could stabilize the Higgs. Others suggest the Higgs might be composite, made of smaller constituents bound together by new interactions. The field's true nature could be the key to unlocking physics beyond the Standard Model. What's truly mind-bending is how the Higgs shapes cosmic structure. Without mass, particles wouldn't clump under gravity, meaning no stars, galaxies, or planets. Just a thin, uniform soup of particles racing through space. The field's geometry, how it couples differently to various particles, determines the mass hierarchy, from the feather-light electron to the ponderous top quark. This fine-tuning seems almost too perfect. Some speculate the Higgs might interact with dark matter, the invisible stuff making up 85% of the universe's mass. If dark particles also acquire mass through the Higgs, it could explain why the two are so mysteriously balanced. Now, shift your gaze to cosmic neutrinos, ghostly particles that barely interact with the Higgs yet hold clues to the universe's hidden architecture. Billions pass through you every second, remnants of the Big Bang and violent stellar explosions. Unlike electrons or quarks, neutrinos have vanishingly small masses, 1,000,000 times lighter than electrons. The Higgs gives them mass too, but through a different, more elusive mechanism we don't fully understand. Even stranger, neutrinos oscillate between three types: electron, muon, and tau, as they travel, implying their masses are quantum superpositions. Some theories suggest heavy, sterile neutrinos, not part of the Standard Model, might mediate this process, offering a bridge to dark matter or extra dimensions. The patterns in neutrino behavior are eerily mathematical. Their oscillation probabilities follow precise angles θ12, θ23, θ13, measured to decimal places in experiments like Super Kamiok and Ice Cube. These angles hint at a deeper symmetry, possibly tied to the Higgs field's own geometry. If neutrinos are their own antiparticles, Majorana particles, as some experiments suggest, it could explain why the universe has more matter than antimatter, a cosmic imbalance written into the Higgs neutrino interplay. What emerges is a breathtaking connection between the infinitely small and the astronomically large. The Higgs field, by giving particles mass, set the stage for gravity to sculpt galaxies. Neutrinos, nearly massless yet ubiquitous, weave through this structure, tracing the universe's hidden scaffolding. Together, they form a dance of symmetry and breaking, order and chaos, a reminder that the cosmos' most profound designs are often written in particles we can barely detect. Cosmic neutrinos are the universe's most elusive travelers, ghostly particles so insubstantial they can pass through light years of lead without a trace. Born in the hearts of exploding stars, black hole jets, and the fiery aftermath of the Big Bang, these nearly massless messengers carry secrets from the most violent corners of the cosmos. Imagine a particle so indifferent to matter that billions stream through your body every second, leaving no wake, no ripple, as if they were shadows cast by another dimension. Yet when we finally catch them, like the high-energy neutrinos detected by IceCube buried deep in Antarctic ice, they bring stories of cataclysms billions of light years away. One of the most startling discoveries came in 2017, when a single neutrino dubbed IceCube 170922 arrived with a cosmic address, its path traced back to a blazar, a supermassive black hole spewing jets of radiation 4 billion light-years away in the constellation Orion. This wasn't just a lucky catch, it was a revelation. For the first time, astrophysicists could pair a neutrino's origin with an observable cosmic event, proving these particles are celestial breadcrumbs leading us to the universe's most energetic phenomena. Even more intriguing are the neutrino bursts that coincide with gamma-ray bursts or gravitational wave detections, suggesting a hidden link between these disparate cosmic signals. When the neutron-star collision that shook spacetime in 2017 also emitted a faint neutrino pulse, it hinted that these particles might be the universal translators of extreme astrophysics, bridging gaps light alone can't cross. But neutrinos don't just point to cosmic violence, they might also sketch the universe's hidden architecture. Because they barely interact with matter, they travel in near-perfect straight lines from their sources, unaffected by magnetic fields or interstellar dust. This makes them ideal probes for mapping otherwise invisible structures, like the dense cores of active galaxies or the turbulent regions around black hole accretion disks. Some theorists even propose that neutrino hotspots, clusters of detections from specific directions, could trace dark matter's distribution, as decaying or annihilating dark particles might release these ghostly signals. The geometry of neutrino behavior is its own enigma. They oscillate between three flavors: electron, muon, and tau as they travel, a quantum quirk implying they have mass, albeit vanishingly small. The angles governing these oscillations, measured to exquisite precision in labs like Super Kamiokande, follow mathematical symmetries that might connect to the Higgs field or even extra dimensions. There's even a tantalizing anomaly. Certain neutrino experiments detect more oscillations than the standard model predicts, sparking speculation about a fourth, sterile neutrino, a hypothetical particle that could open doors to entirely new physics. Now shift your gaze from these ethereal particles to a structure where time itself takes on crystalline form: time crystals. Unlike neutrinos, which slip through space unnoticed, time crystals are a revelation of symmetry rewritten, a phase of matter that breaks time's uniformity, just as ordinary crystals break spatial symmetry. Imagine a clock that ticks forever without energy input, or a snowflake that cycles through its patterns in perpetual motion. This isn't science fiction. It's a quantum phenomenon first created in labs in 2017, where atoms pulsed in predictable, repeating patterns without losing energy, defying the usual march of entropy. What's mesmerizing is how time crystals bridge the abstract and the tangible. In a diamond, atoms arrange in a repeating spatial lattice. In a time crystal, the pattern repeats in time instead of space. The implications ripple across physics, from quantum computers that could leverage these stable cycles for error-free calculations, to simulations of exotic states like cosmic strings or black hole horizons. Some theorists even speculate that time crystals might exist naturally in the extreme conditions of neutron stars or the early universe, their rhythmic pulses echoing like cosmic metronomes. The dance between neutrinos and time crystals might seem distant, but both reveal a universe far stranger and more structured than we once imagined. One flits through space, barely touching reality. The other twists time into loops, challenging our most basic notions of motion and energy. Together, they whisper the same truth. The cosmos is written in geometries we're only beginning to decode. Time crystals rewrite the rules of matter by performing a quantum dance that defies time itself. Unlike ordinary crystals where atoms arrange in repeating spatial patterns like a diamond's lattice, time crystals tick through cycles of motion without losing energy, as if the universe granted them permission to ignore entropy. Picture a clock that winds itself or a pendulum that swings forever without friction. This isn't perpetual motion, it's a delicate quantum phenomenon first theorized in 2012 and later created in labs using chains of ions or diamond impurities. When chilled to near absolute zero and nudged with a laser pulse, these systems don't settle into equilibrium. Instead, they pulse at a rhythm unrelated to the external stimulus, like a metronome that finds its own tempo. What's astonishing is how time crystals bend symmetry. The universe's laws don't care if you run time forward or backward, except here. Time crystals spontaneously break this symmetry, locking into oscillations that distinguish past from future. Imagine flipping a coin and it always lands on its edge, refusing to choose heads or tails. That's the defiance at play. In 2017, two teams, one at Harvard, another at the University of Maryland, built the first time crystals using ytterbium atoms and nitrogen vacancies in diamond. Their experiments revealed a phase of matter that doesn't fit the classical mold, where periodicity isn't imposed by external forces but emerges from quantum entanglement. Could nature have forged time crystals long before we did? Extreme cosmic environments might hold clues. Neutron stars, with their crushing densities and bizarre quantum fluids, could host conditions where time crystallization occurs naturally. The star's superfluid core, a soup of neutrons flowing without friction, might develop rhythmic density waves that echo time crystal behavior. Even the early universe, in its seething plasma state, could have briefly birthed primordial time crystals, fleeting structures that pulsed before dissolving into the chaos of expansion. Some theorists speculate that dark matter, if it includes certain ultralight particles, might form macroscopic time crystals in galactic halos, their subtle oscillations invisible except through gravitational ripples. The quantum foam, a turbulent sea of virtual particles popping in and out of existence at the smallest scales, might also connect to time crystals. If space-time itself has a granular structure, as some quantum gravity models suggest, these grains could exhibit time crystalline properties, ticking through discrete steps like frames in a cosmic film. This wouldn't just reshape our understanding of matter, it would redefine time's very fabric. Time crystals might even serve as quantum memory in advanced civilizations, storing information in their unyielding cycles across eons. What's thrilling is how this discovery blurs the line between the quantum and cosmic. A phenomenon born in tabletop experiments could illuminate the universe's most hidden corners, from neutron stars to the birth of spacetime. Time crystals don't just challenge physics, they invite us to imagine a cosmos where matter dances to rhythms we're only beginning to hear. Quantum foam isn't just a poetic metaphor, it's the turbulent, churning foundation of reality itself, where space-time loses its smooth elegance and fractures into a seething sea of virtual particles and wormholes. Picture the surface of a calm lake, serene and unbroken, until you zoom in to see the chaos beneath. Bubbles forming and popping, currents colliding, the water itself boiling with unseen activity. That's the quantum foam, a realm where the very fabric of spacetime rides with fluctuations so violent they defy classical physics. At scales 1 trillion times smaller than an atom, the universe might not be continuous at all, but a frothing, dynamic mesh where space and time flicker in and out of existence like static on a screen. This isn't just theoretical whimsy. Quantum foam could leave tangible fingerprints on the cosmos. When light travels across billions of light years, these microscopic ripples in spacetime might scatter its path ever so slightly, like a flashlight beam shimmering through fog. Gamma-ray bursts, those brilliant cosmic explosions, could hold clues their highest energy photons might arrive at Earth delayed by mere milliseconds compared to their lower energy counterparts, a phenomenon called vacuum dispersion. If spacetime were perfectly smooth, as Einstein envisioned, this wouldn't happen. But if it's foamy, the highest energy photons would slog through the turbulence like a hiker battling thick underbrush, slowing their journey. Telescopes like the Fermi Gamma Ray Space Telescope hunt for these delays, probing the universe's finest structure through the lens of distant cataclysms. The implications ripple outward. If quantum foam exists, it blurs the line between geometry and matter, suggesting that particles themselves might be knots or vibrations in spacetime's fabric. String theory leans into this idea, proposing that what we call electrons or quarks are just resonant frequencies of tiny, vibrating strings. Even black holes, those gravitational monsters, could be entangled with the foam. Their event horizons might not be smooth boundaries but fractal-like surfaces, seething with quantum fluctuations that leak information in subtle ways. Some theories suggest that dark energy, the mysterious force accelerating the universe's expansion, could arise from the foam's relentless energy, a kind of quantum pressure pushing space itself apart. Now, shift your gaze from the chaos of the infinitesimal to the enigmatic whisper of action's hypothetical particles that could solve two cosmic riddles at once. These elusive entities, born from quantum field theory, might be the missing pieces of both dark matter and the universe's symmetry puzzles. Unlike the frenetic quantum foam, actions are imagined as ghostly waves drifting through galaxies, their presence felt only through gravity's gentle tug. Actions emerged from an elegant solution to a problem called the strong CP problem, a question about why the nuclear force doesn't seem to care about certain mirror image symmetries. To fix this, physicists proposed a new field permeating space, whose ripples would manifest as action particles. Lightweight and abundant, these particles could have flooded the early universe, clumping into vast halos around galaxies, exactly what we observe with dark matter. Their detection hinges on their faint interaction with magnetic fields, where under the right conditions, an action might transform into a photon, leaving a whisper of microwave light. Experiments like ADMC's use ultra-sensitive cavities to catch these phantom signals, tuning their detectors like cosmic radios searching for the universe's quietest station. What's mesmerizing is how actions weave together the very large and the very small. Their quantum behavior might imprint patterns on the cosmic microwave background, subtle temperature variations that next-generation telescopes could uncover. Meanwhile, their collective gravity sculpts the universe's grandest structures, guiding galaxies into their cosmic web. If discovered, actions wouldn't just fill the dark matter gap. They'd reveal a hidden symmetry woven into the fabric of reality, a delicate balance between chaos and order that shapes everything from quark interactions to galactic superclusters. From the frothing quantum foam to the silent action sea, the universe whispers its secrets in geometries both violent and serene. Each discovery peels back another layer, showing us that even in the darkest corners of space or the smallest folds of space-time, there's a design waiting to be read, if only we learn how to listen. Actions drift through the cosmos like ghostly waves, an invisible sea that might hold the answer to one of science's greatest mysteries, dark matter. Unlike the chaotic quantum foam, these hypothetical particles are imagined as ultra-light, barely interacting with ordinary matter, yet their collective gravity could sculpt the universe on the grandest scales. Picture an ocean where each drop of water is a single action, trillions upon trillions of them flowing together in vast, coherent waves. These waves wouldn't crash or break like earthly tides. Instead, they'd ripple through galaxies, subtly guiding the motion of stars and the formation of cosmic structures without ever making their presence directly known. The elegance of actions lies in how they solve two puzzles at once. First, their existence would explain why the strong nuclear force, the glue holding atomic nuclei together, obeys a peculiar symmetry called charge parity conservation. Without actions, this symmetry seems unnaturally perfect, as if the universe arbitrarily decided to ignore certain mirror image possibilities. Theorists suspect actions act as cosmic peacekeepers, gently nudging particle interactions into balance. Second, and more tantalizing, these particles could be the missing dark matter, their combined gravitational pulls shaping the rotations of galaxies and the architecture of the cosmic web. Simulations show that action dark matter wouldn't clump like traditional particles, but instead form diffuse, wave-like halos around galaxies, a perfect match for observations that baffle conventional models. Detecting actions is like trying to catch whispers in a hurricane. Their interactions are so feeble that they pass through Earth and our detectors as if they weren't there. Yet scientists are devising ingenious traps. Experiments like ADAMS use powerful magnetic fields to coax actions into revealing themselves. Inside a supercooled cavity, actions might convert into faint microwave photons, a signal so delicate it requires quantum amplifiers just to be heard. Other approaches hunt for action-induced distortions in starlight or subtle shifts in the spin of atoms. The quest is a high-stakes gamble. Success wouldn't just confirm a new particle, it would rewrite our understanding of mass, gravity, and the universe's hidden blueprints. Now shift the lens to the ekpyrotic universe, a theory where the cosmos isn't born from a single Big Bang, but from a collision between higher dimensional membranes. Imagine two sheets of reality floating in a higher dimensional space, slowly drawn together until they touch. The energy of their impact ignites our universe's expansion, not as a singularity, but as a fiery rebirth from a previous cosmic cycle. In this model, actions take on a new role. Their wave-like nature could be imprinted by the geometry of these colliding membranes, their oscillations reflecting the resonant frequencies of the collision itself. The universe's large-scale patterns, the distribution of galaxies, the voids between them might carry echoes of that primordial encounter. What's striking is how these ideas converge. The ekpyrotic scenario naturally produces ultra-light particles like actions, while action waves could explain why the universe appears so finely tuned. Their collective motion might even seed the quantum fluctuations that grew into galaxies. It's a vision where the cosmos isn't just expanding but vibrating. Its history written in harmonics we're only beginning to discern. Whether actions exist or not, their theoretical allure reminds us that the universe's deepest secrets often lie in the interplay between the unseen and the unimaginable. The ekpyrotic universe theory turns the Big Bang narrative on its head. What if our cosmic beginning wasn't a fiery singularity, but a cosmic collision in a higher dimensional arena? Picture two vast parallel membranes called branes, floating in a hidden dimension, separated by an unimaginably thin gap. These aren't just abstract sheets. They could be entire universes, each with their own laws of physics, vibrating in the bulk of higher dimensional space. Over eons, they drift closer until, bang, they collide. The energy of that impact doesn't explode outward from a single point, but erupts everywhere at once, igniting the expansion of our universe like a curtain of fire sweeping across a stage. This is the ekpyrotic scenario, a radical alternative where the universe cycles through phases of collision and separation, avoiding the need for a singularity entirely. What makes this idea so compelling are the fingerprints it might leave behind. Unlike traditional inflation, which stretches quantum fluctuations into cosmic scales, the ekpyrotic model predicts subtle differences in the cosmic microwave background, those faint temperature variations that serve as a snapshot of the infant universe. Specifically, it favors patterns that are less lumpy on large scales, with correlations between hot and cold spots that differ from standard inflationary predictions. Some argue the Planck satellite's data shows hints of this, particularly in the way large-scale fluctuations appear slightly suppressed. If confirmed, it could mean the universe's design isn't just a one-time event but part of an endless rhythm, a cosmic heartbeat echoing across dimensions. But here's where it gets even stranger. The ekpyrotic model doesn't just replace the Big Bang, it redefines time itself. In this framework, our universe isn't the first and won't be the last. Each collision resets the cosmic clock, erasing the past while seeding the future. Black holes from previous cycles might evaporate entirely, their information encoded in the geometry of the colliding branes. Even dark energy, the mysterious force accelerating today's expansion, could be a relic of this cyclical dance, a slow, inevitable pull drawing the branes together for the next collision. Now, shift your focus from the grandeur of colliding universes to the faintest whispers of spacetime itself, holographic noise. If the universe is fundamentally a hologram, as some theories suggest, then at the smallest scales, spacetime shouldn't be smooth but grainy, like static on an old television. This isn't just theoretical musing. Experiments like GEO 600, a gravitational wave detector in Germany, have hunted for this noise. The idea is simple. If space-time is pixelated, then very precise measurements should reveal a faint fuzziness, a quantum jitter at the Planck scale. So far, the signal remains elusive, but the search continues, with next-generation detectors promising unprecedented sensitivity. What ties these ideas together is their challenge to our most basic assumptions. The ekpyrotic model questions whether time has a true beginning, while holographic noise suggests space itself might be an illusion, a projection of information stored on a distant boundary. Both hint at a universe far stranger and more interconnected than we ever imagined, where the fabric of reality is woven from deeper, hidden threads. As we peer into these mysteries, we're not just uncovering the universe's secrets, we're redefining what it means to exist within it. Holographic noise might be the universe's way of revealing its deepest secret, that spacetime itself has a pixelated structure, a fundamental resolution limit like the graininess of an old photograph. Imagine zooming in on reality until the smooth fabric of space and time fractures into a seething foam of quantum fluctuations, where distances shorter than a trillionth of a millimeter lose all meaning. This isn't science fiction. Experiments like GEO 600, a gravitational wave detector in Germany, have hunted for this telltale fuzziness, a statistical static in their measurements that could betray the universe's digital underpinnings. The idea stems from the holographic principle, which suggests that all the information in a three-dimensional volume of space might be encoded on a two-dimensional surface at its boundary, like a cosmic DVD where the data for an entire 3D movie fits on a flat disk. If space-time is pixelated, it would mean that black holes, those cosmic information shredders, aren't the only places where reality gets compressed into bits. Every cubic centimeter of empty space could be buzzing with holographic noise, a quantum scale flickering where tiny regions of space pop in and out of existence. Some models predict this noise would manifest as a faint, high-frequency jitter in laser interferometers, the same devices used to detect gravitational waves. The challenge: this signal would be drowned out by thermal vibrations, seismic noise, even the quantum jitter of the laser light itself. Yet the hunt continues because finding holographic noise wouldn't just confirm a theory, it would rewrite our understanding of reality, proving that the universe operates like a vast, hyper-advanced simulation. Now pivot from the idea of cosmic pixels to an even more unsettling possibility: vacuum decay. The universe's vacuum isn't just empty space, it's a seething quantum field brimming with potential energy. Think of it as a valley in a vast energy landscape, where our current vacuum sits in a stable but not necessarily lowest energy state. What if there's a deeper valley, a true vacuum with far less energy? A random quantum fluctuation could theoretically kick the universe over the edge, creating a bubble of true vacuum that expands at the speed of light, rewriting the laws of physics as it goes. This isn't a gradual change, it's an existential reset button, where the bubble's boundary would appear without warning, leaving no time to react. One moment, stars shine and life thrives. The next, fundamental constants like the strength of electromagnetism or the mass of electrons shift catastrophically. Atoms disintegrate, chemistry as we know it ceases to exist. The eerie part, vacuum decay, might already be underway somewhere in the cosmos, and we wouldn't know until the bubble reached us. The trigger could be as simple as a high-energy particle collision in a distant galaxy, or as exotic as a black hole's quantum fluctuation. Some theories even suggest that the Higgs field, the same field that gives particles mass, might be metastable, perched precariously on the edge of such a transition. CERN Large Hadron Collider has scrutinized the Higgs boson's properties for clues, searching for any hint that our vacuum is a ticking time bomb. Yet there's a strange beauty in this fragility. The universe's apparent stability might be an illusion, a temporary equilibrium in an endless landscape of possibilities. If holographic noise reveals the pixelated scaffolding of reality, vacuum decay reminds us that even the cosmos's most fundamental rules aren't set in stone. Together, they paint a picture of a universe far more dynamic and uncertain than we ever imagined, one where the patterns we take for granted could dissolve in an instant, rewritten by quantum chance or hidden geometries we're only beginning to glimpse. Vacuum decay isn't just a theoretical curiosity, it's the universe's ultimate reset button, lurking in the quantum fine print of reality itself. Picture the Higgs field not as a static backdrop, but as a valley nestled between towering energy peaks. Our universe sits comfortably in this valley, where particles acquire mass and physics follows familiar rules, but hidden beyond the ridges might lie a deeper chasm, a true vacuum where the Higgs field could drop to a lower energy state. If this transition ever occurred, even in a microscopic patch of space, it would unleash an expanding sphere of annihilation. The boundary of this bubble would race outward at light speed, rewriting the laws of physics in its wake. Atoms would dissolve, stars would blink out. The very constants governing reality, the strength of gravity, the charge of an electron, might morph into alien values. By the time the light from this event reached us, it would already be too late. This isn't science fiction, it's a genuine possibility baked into our best models of particle physics. Calculations suggest the Higgs field's current state might be metastable, like a pencil balanced on its tip. Quantum fluctuations or high-energy particle collisions could provide the nudge needed to topple it. CERN Large Hadron Collider has scrutinized the Higgs boson's mass for clues, finding it perilously close to the threshold between stability and catastrophe. Some theorists argue this fine-tuning is evidence of a multiverse, that countless universes with random Higgs values exist, and we simply inhabit one where the pencil hasn't fallen yet. Others propose undiscovered particles might stabilize the field, acting like invisible fingers steadying the cosmic balance. The geometry of vacuum decay is eerily beautiful. The bubble wouldn't expand like an explosion, but as a perfect, shimmering sphere, a flaw in spacetime's fabric smoothing itself out. Advanced civilizations might detect its approach through subtle distortions in quantum entanglement or shifts in fundamental constants. Yet for all its destructive potential, vacuum decay could also be a creative force. Some models suggest new universes might bud from these events, each with reborn physical laws, a fractal rebirth where one cosmos's end becomes another's beginning. Now shift your perspective from universal annihilation to universal awareness. If the cosmos can encode information in black hole horizons and quantum foam, could it also harbor something resembling consciousness? The geometry of awareness might be woven into reality's deepest layers, from the self-organizing patterns of neural networks to the way galaxies mirror the brain's synaptic web. When a single proton spin can influence another across light years through quantum entanglement, the line between physics and perception blurs. Perhaps consciousness isn't an emergent property of brains, but a fundamental feature of spacetime itself, waiting to be unlocked by the right configurations of matter and energy. Consciousness might not be just a byproduct of the universe, it could be woven into its very fabric. This radical idea, known as panpsychism, flips our understanding on its head. Instead of asking how brains create awareness, it proposes that consciousness is a fundamental property of reality, like space or time. Think of it like this: just as electrons carry charge, perhaps all matter carries some faint spark of experience, a whisper of subjectivity. The intricate patterns we've explored, the golden ratio in galaxies, the fractal branching of cosmic webs, even the rhythmic pulses of time crystals, could be more than mathematical curiosities. They might be echoes of a universe that isn't just operating mechanically but experiencing itself. Consider the way information flows in the cosmos. A single photon's path isn't predetermined. It's a dance of probabilities until observed. Quantum entanglement links particles across vast distances, their states interdependent in ways that defy classical intuition. These phenomena don't just challenge physics, they hint at a universe where observation and existence are intertwined. Some interpretations of quantum mechanics, like the von Neumann-Wigner hypothesis, even suggest consciousness plays a role in collapsing probabilities into definite outcomes. While controversial, these ideas force us to confront a haunting question. Could the universe's order emerge not from blind laws alone, but from a kind of cosmic mindfulness? The parallels between neural networks and cosmic structures deepen the mystery. The human brain's neurons branch in fractal patterns strikingly similar to the universe's filamentary web. Both systems optimize for efficiency, whether transmitting electrical signals or gravitational forces. Is this mere coincidence, or does it reflect a deeper symmetry between inner and outer worlds? Philosophers like Alfred North Whitehead argued that reality is a process of experience, with even atoms possessing a rudimentary form of feeling. In this view, galaxies might not just exist, they might, in some ineffable way, know they exist. Yet skepticism is vital. Science thrives on testable claims, and panpsychism's nebulous nature makes it resistant to traditional experimentation. But the echoes persist. The universe's self-organizing complexity, from star formation to biological evolution, resembles a system learning, adapting, even creating. If consciousness is indeed fundamental, then every spiral nebula, every orbiting planet, every quantum fluctuation could be part of a vast, unfolding awareness. As we conclude this journey, one truth remains. The cosmos is far stranger and more interconnected than we ever imagined. Whether through the lens of physics, mathematics, or philosophy, the patterns we've uncovered invite us to see the universe not just as a cold, empty machine, but as a living, evolving tapestry, one that might just be awake. And in that awakening, we find our own place, not as passive observers, but as participants in a grand, mysterious dance of consciousness and design. From the golden ratio to the cosmic web, the universe's designs reveal a breathtaking interplay of order and chaos. These patterns are not just beautiful, they're clues to the deepest mysteries of existence. As we continue to explore, each discovery peels back another layer of the cosmic blueprint. The night sky is more than stars. It's a canvas of intricate artistry, waiting for us to decode its secrets. Keep looking up and remember, the universe's most profound designs are still being revealed. What's astonishing isn't just the existence of these patterns, but how they connect across scales. The same spiral that shapes a galaxy echoes in the curve of a seashell, while the branching veins of a leaf mirror the vast filaments of the cosmic web. This isn't coincidence, it's a testament to the universe's love of efficiency, reusing the same mathematical blueprints wherever they work. The golden ratio optimizes growth, fractals maximize surface area, and orbital resonances stabilize systems. From the quantum foam to galactic superclusters, nature adheres to a hidden playbook written in geometry and probability. Yet for all its precision, the cosmos thrives on balance. Too much order, and the universe would freeze into static perfection. Too much chaos, and structure would never form. Instead, we live in a world where black holes spin with razor-sharp precision, while nebulae bloom in turbulent splendor. Even time itself pulses rhythmically in crystals and decays unpredictably in quantum foam. This delicate dance between predictability and surprise is what makes the universe so fertile, able to birth stars, planets, and life itself. The more we learn, the more we realize how much remains hidden. Dark matter's invisible threads, the holographic principle's cryptic code, the fleeting whispers of actions. Each discovery opens new questions. But that's the thrill of the hunt. Every telescope pointed skyward, every particle detector buried underground, is a bid to eavesdrop on the universe's grand conversation. And what we've heard so far is extraordinary. A story of symmetry breaking and entropy, of chaos birthing order, and of patterns so deep they might be written into the fabric of reality itself. So the next time you step outside and gaze at the stars, take a moment to marvel not just at their light, but at the hidden architecture behind them. Those pinpricks of light are part of a tapestry woven with dark matter, stitched together by gravity, and animated by forces we're only beginning to understand. The universe doesn't just exist at designs, iterating over billions of years, refining its structures with each passing epoch. And we, by some miraculous stroke of luck, are here to witness it. The journey doesn't end here. With every breakthrough, from the Event Horizon Telescope's first black hole image to the quantum vibrations of time crystals, we're handed new pieces of the puzzle. Some will fit neatly into place, others might force us to redraw the entire board. But that's the beauty of exploration. The cosmos isn't a static museum exhibit. It's a living, evolving masterpiece, and we're all invited to join the search for its secrets. So keep wondering, keep questioning, and above all, keep looking up. The universe has far more to show.